Hello grade 12s, as promised we're going to do some revision for paper 1 and we're going to take this paper from the EC and see what it can do to assist in your revisions. Okay, so we'll start with the MCQs, but we first have to handle some instructions. It's very important to make sure that this trio is internalized in your brain during the exams, and it should be easy to navigate between these. So the rounding off here, it's a minimum of 2 decimals, meaning we can do more than 2 but not less than 2. And then of course, if we are to motivate for anything here, we need to keep it as brief as possible. We don't go to town. Okay, great. So first question, the local instruction tells us that there's only one answer to be chosen, or at least write only one answer. Okay, there may be a situation where there's more than one correct answer. The examiner is probably trying to check you out whether you adhere to instruction or not by choosing only one correct answer. But if you find that there's more than one answer and then the answer proposed is different, then it means there is a problem with the question, the examiner, whether they didn't get their very own idea correctly, or maybe the typist actually put the wrong symbol as the answer. It happens, so be very careful, especially with provincial papers. These are notorious for errors. All right, so 1.1 says a trolley moves on a flat horizontal surface when a constant force. Now what is important is to know that this is flat, it's not elevated, and it's a straight line, it's a horizontal. Okay, by a constant force is applied to it. And if we look at this one, we see that this is a smooth surface. How do we know it's a smooth line? Because if it is not broken, or at least you see things like that, then it indicates there is no friction. Okay, so this is the smooth surface, and now if this is the only force acting on this object, it becomes what we call the resultant force. Okay, now what do we know about the resultant force? Newton's second law tells us that it is equal to mass times acceleration. Okay, now what do we know? Acceleration is directly proportional to the resultant force, right? Right, and also acceleration is inversely proportional to the mass of the object, or you can say directly proportional to the reciprocal of the mass. Okay, so this is spelling out Newton's second law. Can you see? Now, one needs to know the definition of the law itself and be able to give some information. Now, folks, if we are suggesting that acceleration is present and our force is constant, so since these two are directly proportional, it means we will also have a constant acceleration. Sometimes we use the word uniform acceleration. So this means this is constant acceleration. Or sometimes we call it uniform. Okay? Meaning it does not change. Now, if we've got acceleration, what are we doing? We know that the velocity keeps on increasing at the same rate, which is that of the acceleration. So this is essentially what we can gather from the statements given. Now we are told which one of the following physical quantities, how many do you guys know? Vectors versus scalars, and then of course we've got different examples of each, will always remain constant while the trolley is moving. Is it momentum? Well, we know that momentum is the product of mass and velocity. But since our velocity is constantly increasing, or should we say it increases at the same rate, this implies that our momentum will also increase, because we see that momentum is directly proportional to the velocity. And so if the velocity increases, the momentum increases, so it doesn't remain the same. So that's not the answer. Is it acceleration? Well, we know acceleration is directly proportional to the resultant force, and if this is constant, and so the acceleration will be constant, and therefore this is true. Okay. Kinetic energy, we know that EK is the product of 0,5, the mass of the object, and the square of the velocity. But we can see that the velocity is increasing with mass and the half being constant. So from here, we understand that obviously EK is directly proportional to the square of the velocity. Alright, so this means as the velocity increases, in fact, if we can just draw a velocity versus kinetic energy graph, since this is on a square, this is a graph that we would get. It's a parabolic graph that is restricted to the positive, or at least to the first quadrant. Alright, so we will appreciate that as the velocity increases, EK also increases, like that, in a parabolic manner. Okay, so it's not the answer. What about gravitational potential energy? So we know that EP is equal to mgh. Now we know that this is mg, but now h, this is the flat surface, is 0. So this will always be 0, no matter where we are. Of course, as long as the statement has given us that parameter, this is the state of motion of this object. So we can see that we've got two candidates here for the answer. It's B and D. Okay, so that means you follow the instruction, you choose only one. Okay, but do double check with the memorandum, because when there's this situation, there's usually an error rather than this being the intention. It's hardly this case, but be very careful. It can come when you least expect it. But then if the memo says something different, then again I said it means there is a problem with the construct of this question, or maybe the typist put the wrong symbol, or even the examiner was confused. It's possible. Okay. Now let's move on. A sphere is attached to a string, right, which is suspended from a fixed horizontal bar, right? Great, as shown in the diagram below. So obviously we know that on the string we're going to have the tension, right? And then we will have the force of gravity doing its own things there. So that's essentially the story. Now maybe let's show it on a free body diagram rather. So we will have tension going up and Fg going down. All right. Okay, all right. Now what do we see? We know that this is suspended. Now suspension means it's hanging stationary, meaning it's not moving. So we need to understand certain terminologies, right? But now if this is the case, it means the tension is equal to the gravitational force downward. Okay, good. Now the question says the reaction force. The reaction force now to the gravitational force. Now once you hear the word reaction, we are already talking about Newton's third law, where we talk of action and reaction. Okay, now we're saying the reaction force to the gravitational force exerted by the Earth on the sphere is there. Obviously, now if you introduce this one and say, okay, there's the Earth, and that's the center of the Earth. Okay, we will see that if the Earth is pulling on the sphere with Fg, the sphere will also be pulling on the earth with minus Fg, right? Because it will be equal in magnitude but opposite in direction according to Newton's third law. So please guys, be very familiar with these things because they can hurt if you don't get them right, okay? So obviously it's going to be the force of the sphere on the earth, okay? That's the correct answer. So if you understand the law, you have a bit of an idea of what is going on. You don't need to be looking elsewhere. Now this is the best question for this type of a question. I don't like it when there's an interface right underneath the object we're looking at because there's too many forces interfering there. But hey, as long as you get the physics right, it's already okay. But I worry sometimes when things are not making sense because the setup has to be conducive for someone to apply their knowledge without too much interference. But hey, the examiners will do their own thing, so let them do it. It's fine. So this one is a straightforward answer. As long as you understand the question and you probably can identify the law being applied, it makes life a lot easier. Now, the position versus time graph below shows the motion of an object in a vertical direction. Okay, so what do we see? Now, this is not correct to write delta x, but delta y. See, examiners, they themselves are somewhat confused. Anyway, what we will notice is that this is the ground zero. Yo, iten we yapala kagbi. Yapala pitanda kon, kela kagbi. Maybe the thing is dirty there. Okay, whatever. Now, what is going on? We are starting from a height already. And we go even higher if we would perhaps consider that as the highest point. We are going even higher. So if we're going even higher, what does it mean? It means we have some initial velocity, which is not zero. It's some x value. So this means we gave this object some initial velocity. So this is giving us the vibes of a projectile. And then it went higher. But now what do we notice on a position time graph? What do we see? Gradients represent velocity. Can you see this is positive, but it keeps decreasing. As we draw tangent lines to our graph, they keep decreasing. Decreasing, this one is zero. And now what does that mean? The velocity at the highest point is zero because the gradients represent velocity. And then they keep going down again until we get to the point where we launched it. The velocity there is going to be the same as the velocity that it left with, right? So this is going to be minus the initial velocity, x, meaning it's a negative version of it, but equal magnitude. And then they continue to drop until we hit the ground. Now when we hit the ground, we will have some final velocity that would be maximum. So that would be the biggest velocity we can hit here. So sometimes questions like these are not ones you can just answer at a go. You have to think about what you are doing. Now obviously folks, now with this statement right here, we are told to take ground as zero reference. All right, nice. Now we can see that indeed that the ground is the zero reference. Now this gives us two scenarios because we are not told to ignore the effects of air friction. So this is a scenario A, which could be talking about a projectile. Okay, and if this is the projectile, that means if we draw a free body diagram, the only force acting would be gravitational force. That would be Fg. And that means the acceleration is g, which is 9.8 meters per second squared downwards. Okay, so that is the idea if this is the projectile. But it could also be option B, where we do not have a projectile, not projectile, meaning we could consider a resistance. Sometimes the question can include that. But now if this is not a projectile, well, we can see that on its way up, on the way up of this object, don't know what it's doing there, we've got two forces, the gravitational force and the air resistance. Remember, air resistance always opposes the direction of motion, okay? So this would be Fg, that would be F of the air, okay? Meaning air resistance. It's not Fa, it's Fa. Now, this would tell us that the resultant is going to be the summation of these two. Now, this is the situation. The resultant force here is going to be bigger. You can just say F res, okay? It's not fresh, but resultant force. Now, if the resultant force is bigger than Fg, what does it mean? It means the acceleration is greater than g. And in which direction? It's going to be in the direction of the resultant force, downwards. So this is the scenario that we could get from before this object reaches its maximum height. And then, of course, until at maximum height also. But as it changes direction, these two change around, because friction always opposes the direction of motion. So we would have F friction going in that direction, and we would have our gravitational force going down, as it often does. But now the resultant force is the difference between the two, and since this is going down, it means the gravitational force is greater than the F friction at first, and so the resultant force is going to be the difference between the two. But it's definitely not going to be equal to the gravitational force. Now, this means our acceleration is definitely less than g, but downward. So, we will be accelerating down, but less than g. Can you see, even if we're not doing a projectile here, we would still be accelerating down. But with projectile motion, guys, we never accelerate until we reach the ground. The air friction, as we keep going faster and faster, it catches up, right? Air friction catches up with gravitational force, so that these two are equal. So we know now we get to a point where F of the air is equal to Fg. Now this means the resultant force is 0. Now if the resultant force is 0, it means acceleration is 0. Now this is the situation when we are doing what is called terminal velocity. Now this is the constant velocity that an object falling from the air or in the air is going to be doing constant velocity when it no longer accelerates, and it will keep this velocity until it hits the ground. Now this is the knowledge we use with parachutes, because parachutes actually decrease this velocity to as small as possible, to avoid someone hitting the ground and crashing onto the ground. Okay, so these are the two scenarios when there is no exclusion of air resistance that we need to think about. Now the question says, which one of the following velocity time graphs? Can you see? Now we're moving from a position time graph to a velocity time graph. As we could see, the velocity decreases until it's 0. So this one starts well. It says we're starting at some velocity v. That's the initial velocity. And this is suggesting that upward was taken as positive. Okay. Now we decrease to a 0 velocity, which is at the highest point. And then it continues to decrease to some velocity. That's also good. But now what do we notice? The gradient is constant in that scenario. This is suggesting more of a projectile. But then we have this section that changes everything. Now, is that correct? Now, if we change direction of acceleration, did we see any change of direction of the acceleration? The answer is no, because our acceleration was downward throughout until it wasn't there at all in the scenario B. So it doesn't change direction. So now this change of direction is incorrect. Acceleration in this scenario will not change direction. It can change its value. meaning instead of being sharp, meaning the same gradient, we saw that with this situation, the acceleration is less than the, the acceleration is less than g. Now, if it is less than g, what do we see? We may see a gradient that is essentially a bit bigger, because I mean a lesser value on the negative is going to be a little less steep. Okay, so this would be something like this. Okay, maybe let's not make it too big. Maybe let's make it like so. We could see something like that, and then it becomes a constant velocity when we're doing the terminal velocity. So this is something we would expect. Rather than a complete change of direction, it would be just a decrease, or rather an increase in the gradient, but we would see no change in direction. So this is what would be, but because of that, it's wrong. Okay, we cannot accept it. Now the second one, we see we're starting at some velocity v. We saw that the initial velocity was there, and of course this is also suggesting we're taking upward as positive, and then we get to the maximum height, so that's good. And then the gradient is acceleration, it's downward, it's a negative slope. Great, but then we have a problem here. It changes direction again. Do we really change direction of our acceleration? No, we don't, but we could change its gradient. Now its gradient would change in this manner, perhaps something like that, and then we do constant velocity, which would be that terminal velocity. So this is what we could expect, rather than a change of direction of our acceleration. So as a result, this is wrong. We look at C. C is suggesting we're starting at some velocity v. That is also saying upward is taken as positive. We decrease to a maximum, that's good. The gradient is constant, it doesn't change. That could also be good for scenario A, a projectile, which is what we deal with, and then we stop here. That would be the best representation. So this is a candidate. We look at the last one. It says we're starting at some velocity minus v. This is when we're taking upward as negative. Okay, now we decrease our velocity to 0, or we increase it to 0, it doesn't really matter, that is good. And then we continue like that, but now the problem comes when we change direction of our acceleration, and we saw our acceleration is always downward, or it's not there at all. So that becomes incorrect, because what we would expect, it's a less steep gradient maybe, and then we do that terminal velocity, which is the constant velocity. Okay, so that would be something like that. Of course, it's not quite perfect now, it's messing with me. Anyway, so as a result, that is wrong. So the best answer here is C, because at least it represents that possibility A. And obviously, guys, you should know that in grade 12, this is the main question. All right, so I hope you guys understand this type of questions. Of course, I'm making it too long, because if you understand this concept, you would already know C should be the answer, because the other ones are changing direction. So if you understand acceleration doesn't change direction in VPM, especially when we don't have an engine that it's doing its own things, meaning it first was doing maybe free fall, or it was just, you know, the engines were switched off and then all of a sudden they changed. But you would see that this graph is suggesting that we never changed direction. We went up, up, and then down, down, down until we hit the ground. So there was no change in the direction of motion after maximum height. We went straight down. So there shouldn't be a change in acceleration. So the clues, as you can see, is understanding this framework and knowing that, okay, whatever happens, we don't expect a change in the direction of acceleration, at least. And that gives a clue, and we can pick C as the best option. All right, a spacecraft made up of two modules, P and Q, of masses 3m and m respectively, is traveling horizontally at a velocity v due east. Okay, now we can choose due east as positive direction. Now an explosion causes the two modules to separate, and we're given this. And remember, this thing can be twisted around. You can find the east put over there, the north over here, the west over here, the south over there. The examiner can play with this compass, so do not fixate on this look, okay? Be very careful. Whenever there's a clue or key given, focus on that particular key. Don't think there's a mistake. Okay, so we can already see here, guys, that the concept we need to apply here is the conservation of linear momentum. Now, these are things you just realize. You don't need to write them down. I'm doing it to emphasize the point here. Now, now we're told module Q continues in its original direction, that is due east, immediately after the explosion at a velocity of 3v. Now, what will the magnitude and direction of module P's velocity immediately after the explosion? So now we need to apply that P before must be equal to P after. All right. So now their masses are added. So this is 3m plus m times v. Okay, this is equal to 3m times v final, right, which we don't know. Then plus, this one is m times 3v. Okay, good. This one is positive because it's in the easterly direction, and we chose the easterly direction as positive. So this implies we will have 4mv equals 3mvf plus 3mv. Okay, now these are like terms. 3mv and 4mv are like terms. We transpose that to the other side, we end up with 3mvf equals just mv, because 4 minus 3 is 1. We normally don't write 1 mv. Then we divide by 3m, we divide by 3m, then the 3m cancels over there or divides out. So we can say the final velocity of our module P is going to be, the m takes the m, it's going to be a third of our initial velocity. All right, so remember this is positive. It came out positive, so that means it's due east as well. Okay, good. Now, what do we see? That is the one, that is the one. So can you see some questions? Yes, they require some calculation using a principle, which is conservation of linear momentum. But after the calculation, you get the answers. There's no need to worry about other options, if your calculation is correct, of course. Okay, 1.5 says a car moves from rest. Now, rest means initial velocity is 0 in a straight line under the influence of a constant resultant force. I really hate this word. I don't know why, but just doesn't give me the good vibes. Maybe it's because it has something to do with the salary, net salary, so that freaks me out. Anyway, which one of the following graphs best represents the net work done? Again, I hate that word, net work done. The total work done. Come on, guys. Stop this nonsense. This is not finance class. Okay, net work done on the car in relation to its displacement. So what do we know? We know that work, right? We know that work is equal to the resultant force times the displacement and the cos of the angle theta. Now, this is just a trig ratio. It has no units, and it doesn't change for a particular angle. So what is going on? We know that the force is constant. Now we can truly explore the relationship between W and delta x. Think of this one. The model that fits this one well is a straight line equation, y equals mx, where m is the gradient because it's constant, the variable x is the delta x, y is the dependent variable, which is the w. So all we know is that if we have a situation like this, we don't have a y-intercept. This is the graph we expect. A straight line graph that passes through the origin. with a positive gradient. Okay, so that's already option B. So you see, if you understand the mathematical model that explains this, because these equations have nothing, or they are actually nothing but related to mathematical functions that we know and studied so well. So if this is clear, if you know what formula governs a particular graph that you're looking at, and you can see how it relates to one another, then you know, I'm home free here. This one, you don't take time. You pick the right one and you move on. All right, a source of sound approaches a stationary listener. What does it do? It approaches a stationary listener. Okay? Now, if it approaches, what is the impression? Even though this one emits a sound of a particular frequency, but this listener, the frequency of the listener is going to be higher than the actual source, because the listener is getting more compressions ahead of the siren, and so he will hear a little bit of what sounds like the sound is increasing. Think of a car that's coming in front of you. As it comes, the sound sounds a bit heavier. Boo, 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 boo. And then when it passes, it's like boo, 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 until it disappears into the distance. And then you see, it sounds as if there's a change in the frequency of that sound, but there isn't. It's just an apparent change. So this is the Doppler effect. Okay, in a straight line at constant velocity, and usually when we're dealing with Doppler effect, this is the dude we're talking about. Now it passes the listener and moves away. If it moves away, now the frequency of the listener is going to appear lower than the actual frequency being given, right? Because there's less compressions behind the siren than there are ahead of it. Okay, in the same straight line at the same constant velocity. See, nothing has changed over there. Now, which one of the following graphs best represents the change in observed frequency against time? Obviously, from 0, when this car was approaching and this listener started noticing it, the frequency would appear higher. And then as it passes them, well, it changes, and as it moves away, this would appear lower. Right. And so, again here, there's no need to go around in circles. This is correct. But if we look at B, just to be sure, we can see that we can't hear a lower frequency and then a higher frequency. So this is unlikely, because we said it moved away. If it moved away, the frequency of the listener should be less than the actual frequency of the source. So this is already wrong here, and that is wrong. These ones are totally wrong because they don't make sense, okay? So this one, again, you don't spend a lot of time doing it because it's straightforward. 1.7 says a small test charge Q, there it is placed exactly halfway between two identical positive charges. Identical in what regard? This word sometimes in physics doesn't make sense, okay? Be very careful of it. Already hear from the examiner in what regard. It's saying two identical positive charges, X and Y, each with the charge Q. Now that is the identical nature of them. They have the same amount or magnitude of charge, as well as the same quality of the charge, which is positive. So that is the identical nature we're dealing with here. Now, as shown below. Okay, great. So obviously, folks, we will understand that there will be an electrostatic force from that positive charge pushing that, and Newton's third law says that one is also pushing that one, right? Right. And we will also have charge X doing the same, because like charges repel. So since they are equidistant and these magnitudes are the same, it means this electrostatic force is the same. This is electrostatic force E by X on Q. This is the electrostatic force Fe by Y on Q. Now, if we just do a nice free body diagram just to see what's going on, the force to the right is going to be the force by X on Q. And then the force to the left is going to be the force electrostatic force Fe by Y on Q. But now we can see these are of equal magnitudes because they are equidistant from the same charges that participate in that force situation. So this means charge Q would not move in any direction, right? So now it says test charge Q will move vertically downwards. Y, that's absolute rubbish. Move towards X, no. No, yes, because the forces in there's no resultant force, is 0. So if the resultant force is 0, and this was not moving already, therefore it means it is not moving at all. But if this was already moving and the resultant force was 0, it means it would continue at a constant velocity. Okay, this is marrying Newton's first law and second law. Nice. So again, this one, if you understood the construct of the question, it's easy to work around it. Now 1.8 says the internal resistance of a battery in the circuit diagram below is negligible. So what do you know about the word negligible? It means too small. It is insignificant. Okay, so obviously even the wires, the connecting wires, have negligible resistance, because if they were to carry a resistance, the wires would be hot and we would lose a lot of momentum in moving those charges into the desired transformers or to the distances they have to travel. So we always choose things that have very small resistances so that there's almost none. Then charge are almost moving freely, okay? So the antonym to negligible is infinite. Infinite. Now when we say something is infinite, it means it's too large to measure. Right? As infinity. Now usually this is devices like the voltmeter. The voltmeter has infinite resistance, meaning there is no charge that passes through a voltmeter. So in a circuit, there will never be a branch of charge that is passing through the voltmeter. It does not allow it. Whereas an ammeter is more like a variable resistor in a way, because if the pressure of the charges passing through is higher, it increases its resistance so that it can measure exactly the force in which the charge is passing through. And if it is less, it decreases its resistance. So it's more like a variable resistor if you think about it, because the idea it is for it to measure how much charge is passing through. Okay, the lesser the current, the lesser will be the resistance of the ammeter. The higher the current, the higher will be the resistance. It almost matches, the flow of charge per se. But a voltmeter doesn't care. It doesn't. Okay, it just measures the potential difference. What is the potential across 2 points? All right, of course, we always move from higher to lower potential. Nice. Okay, all right, okay. So now we see our circuit. We know that the longest bar is the positive terminal and the short bar is the negative terminal. So from conventional current, we know our current passes through this way, comes through this resistor, and then it passes through that resistor because the circuit is complete. Don't worry about that switch, it doesn't do anything. And then of course the current passes through back into the battery. Now, what we will notice is that these two resistors are of equal magnitude, at least because they are all denoted by the capital letter R. So if we are saying the internal resistance is insignificant, it just means the external voltage is literally the EMF, basically. So what do we see? This voltmeter, because these are equal, they will divide equally that EMF. So this voltage will read half the EMF. And if we were to connect a voltage, that would also read half the EMF, right? But now we didn't put a voltage detector here, but we instead put a switch. But either way, we know, even though it's not there, if we put it, it's going to measure half the EMF, okay? Great. That's the scenario. Now the question says, when the switch S is closed, which one of the following represents the change in the voltmeter and the ammeter readings? Now this becomes interesting, is it not? So we know that, well, the voltmeter is equal to the current times the resistance. But now this is basically the EMF. So the EMF remains constant. So this means our voltmeter is constant. Now what happens when we close this switch? The current branches now. Instead of going through that resistor, it comes down here because this one is eliminated. Because remember, current always wants the least resistance. So the connecting wires have negligible resistance. So all the current is going to pass through there and bypass that resistance. And then it will reconnect here. Okay? So this means we will lose that resistance. So what happens to the total resistance of this circuit? It's dropping. Obviously, for the same EMF, what should the current do to measure up to the same EMF? It has to increase. So now the question is, what would be this EMF? I mean, if this was initially half, since this is the only resistance, now it will measure the EMF. Because obviously with an increase in current, same resistance, we might have a value equal to the EMF. So you can see this is an increase from half to EMF. But what happened to the current? Whatever it was, it has increased. So the voltmeter increases, right? And what happens to the current? It also increases. So now we already see that, okay, these ones are already wrong. Which one ticks all the boxes? It's D. So again, guys, know the law that governs things. And remember, for one to be able to assess the relationship between two variables in an equation, one of the variables involved must be a constant. Okay, great. So this is essentially the story that we get. Nice, 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 nice. Now, what type of an equation is this? Can you see these two are changing? This is more like a hyperbola when we have xy is equal to some value r, 4. But of course, we can say a constant c if we like. This c is a constant, right? So this is more of a hyperbola. Because if we make, for example, I the subject, we would end up with v over r. Can you see v is a constant? It matches that constant c. And now we have a hyperbola, basically. So know these things, guys. So basically the model to this equation is nothing but xy is equal to some constant, meaning it's a hyperbolic function. This is why we talk of the things we talk of. So again, I'm just trying to expand your knowledge to make you realize that you don't study maths for fun and just to pass it. You study it to apply it in some real life situations. Okay, let's move on. 1.9 says, in the graph below, the solid line graph represents how the EMF produced by a simple generator changes with time. Okay, so we can see the solid line over there. And then now the dotted line graph shows the EMF of the same generator after a change was made. Okay, so what do we see? Now if we look, remember we just focus on the period. Always look on that sometimes. The period is the time it takes to complete one cycle. Remember, this represents a sine wave. Remember that. With the AC generator, think of the sine graph. So the full wave is like that, and that would be the period. Okay, so can you see we completed our period at 0,1 seconds. But now when the change was made, we end up with a period completed in half the time. Can you see the period has now taken half the time, which is 0,05. So we halved the period. So now what do we know? We know that the EMF, according to Faraday's law, is minus the number of turns multiplied by the change of phi, all divided by the change in time. Okay, great. But now we are manipulating the time. We can see that we halved the time. So we would say, well, whatever this is, now we want to find out how is it related to EMF. This is going to be minus n times the change of phi, all divided by, now we halved the time, so we're going to say delta t divided by 2. That means 0.05 is half of 0.1. Now, using our fancy equations, we know that we simply multiply with this thing flipped. This is the same as minus n times the change of phi multiplied by, we flip this one when we multiply delta t. So what happens? We end up with minus n times 2 into the change of phi, all divided by basically delta t. Now we can make the 2 go in front. This is the same as minus n times change of phi, all divided by delta t. Can you see what did we just do? We doubled our EMF. Okay, that one is not so nice. Now what do we see? We definitely doubled the EMF from 10 to 20. So this is good. So if we read this, this is 2 times, this represents the EMF E. So can you see? Knowing how to manipulate these equations is very interesting, because these are some of the tricks that the examiners choose to give you as a student. So know how to deal with waves, their periods, and use formulae as well. This is all grade 10 work. Now it says that what change was made to produce the results on the dotted line. We can see that we noticed that the period changed. So obviously, if the period changed, what does it say? Is the speed of rotation halved? Well, we don't know. Is the speed of rotation doubled? Perhaps. Is the split ring commutator added? That's absolute rubbish. More brushes were added. That's nonsense. So we need to deal with those two. So what happened? Now remember, guys, when we're saying the change of phi, the rate of change of phi tells us about, it's a surrogate marker for the speed of the coil. This is used as the surrogate measure of the speed of the coil turning. Okay, now the speed of rotation of the coil, perhaps, maybe I should have said that, the speed of rotation of coil, because for us to get the change in phi, we need to rotate the coil in the magnetic field. So that rate already gives us an indication, because change of phi is saying is the change in the magnetic field over the change in time. And that is a surrogate. It's not a true measure of the actual speed, but it gives us the indication, because the rate of change of phi is going to be the same as the change in the speed. Okay, great. So obviously, if we focus on that, now we just reverse this back and say, okay, this portion here, can you see? Because the number of turns may have not changed. So can you see we doubled the speed? Because if we double this rate of change, we are doubling essentially the surrogate measure of the rate, of the speed of rotation. So this becomes the correct answer. So some questions can be technical, okay? So you need to be very careful, and obviously it is not halved, it is doubled, because if we double the speed, we actually double the EMF, as you can see. So now you need to understand certain things at a deeper level. So sometimes I like these EC papers because they have a tendency to be very low-key, challenging questions. And someone who's not suspecting can easily trip and fall here. But what I like is that it gives you a better understanding of the subject, but in a more reachable level, so to speak. Anyway, let's move on, guys. We don't want to spend too much time. Let's do the last one. It says now, when an excited electron, okay, where do we find electrons in an atom? So think of an atom according to Dalton's, is it Dalton's model? There is our nucleus. It's Niels Bohr. It's actually a Niels Bohr model, okay? Now we will have our electrons in their orbits doing their own thing. They're trying to move around. Obviously, we know that the ones closest to the nucleus, because the nucleus is positively charged, The ones closest to the nucleus move less because they are tightly bound to the nucleus. The ones that move the most are the ones that are far away. That is the outer energy levels. And therefore, those would be the valence electrons. So think about these models, man. They will help you picture what is going on. Now remember, for an electron to be excited, it means this atom must also be excited. Because these are the so-called subatomic particles, so it can't just be excited alone. That means this atom must be excited, even though we know the ones that will benefit from that excitement is the valence electron, or the electrons in the outer energy levels. Because the inner energy levels are closer to the nucleus, they are tightly bound, so they cannot really be energized. You need a lot of energy to strip those electrons of those orbitals to jump into other orbitals. But these ones can do it because they are free. They're relatively free because the distance, remember the electrostatic force according to Coulomb's law, the greater the distance, the smaller will the force be. The shorter the distance, the stronger the force will be. So again, can you see it marries a lot of these concepts that we already have. All right, so this one says this electron moves from higher energy level to a lower energy level. Now, folks, from an excited atom, what do we get? The atom moves from low energy. Remember, atoms cast the spectrum. Of course, through their electrons, right? Because those are sort of like waves or energies. Now, it casts spectrums through those electrons. But a spectrum on its own, it's from the entire atom when most of those electrons participating are doing their thing, okay? So now when an atom is excited, what spectrum do we get? It's an absorption spectrum. And we know the absorption spectrum is discontinuous because not all the frequencies are absorbed, but there are some empty bars or empty lines that represent those frequencies that were absorbed. But now, this electron, because it's in an excited atom, meaning we have an absorption spectrum. Now, when it falls back to ground level, meaning this electron, for some reason, it went up to this level. So it went up to this level, maybe the next energy level that it could reach. But then when it reverts back to the same baseline, which is there, what happens to this electron? It emits light. So we will then emit light, meaning there's gonna those empty bars perhaps that were responsible because of this electron escaping into even higher energy levels. When it goes back to baseline, it releases that energy as a form of light or some frequency. Then we end up with an emission line, né? Because it's just one single electron, so it will give us a line rather than a spectrum on its own. So now it says, when an excited electron moves from a higher energy level to a lower energy level, a specific line, emission line, yes. In an emission spectrum, no. Why? Because we know that an electron cannot just be excited when the atom is not itself excited. And an excited atom casts an absorption spectrum. Okay, so this is not going to be in the emission spectrum, because in the emission spectrum, remember, we get a continuous spectrum, so you don't see anything. Even if there was an electron missing, when it comes back, you won't even notice here. So that would not work. But an emission line, yes. In an absorption spectrum, yes, I would accept that. So some questions are very technical, guys. So as a result, that becomes our best answer. So it helps to understand the concept deeper than just, cramming easy things, red shifts, blue shifts, cramming, emission, spectrum, there's empty bars, and then emission, there's a continuous dons, and then in the what, there's what. No, you can't just cram those things. You have to show understanding, okay? It is important. Now, Since we have finished our MCQs, let us carry on with the long questions. All right, let's move on to question 2. Now this is when the action begins. Now MCQs can actually box you guys, but I think after MCQs it is nice to just go straight to question 2, at least to start the travel day. But what I said to you in the past is that MCQs, guys, are almost always a window into the long questions. So if you understood those concepts examined in the MCQs, these are the same concepts that are going to be examined in the long section. It never works the other way around. Perhaps there may be more into them, there may be less, but what is important is you will notice that what we've done in the MCQs is exactly what we're going to be handling here. Now let's start. Question 2 says a block of mass 4 kilograms is held at rest. Now if it is at rest, what do we know? Initial velocity is 0. There's no resultant force. And that means no acceleration. And this means equilibrium. If we use the technical term, equilibrium. Nice. But be very careful. This one may not necessarily mean rest, but it does apply to rest. It also applies to moving at constant velocity. So these are very important. But rest in literal terms specifically and always means velocity of 0. Okay? But the dynamics of resultant force and acceleration and equilibrium can be a bit confusing, because on a moving object at a constant velocity, there's no resultant force, there's no acceleration, and the forces are in equilibrium, but we are in motion. So Newton's first law is quite flexible. Be very careful about it. Okay, the block is connected by a light inextensible string. Now, light means no weight added. Inextensible meaning it does not stretch, and therefore when these start moving, they move at the same rate. And then that means also the tension at any given point on the string is going to be the same. Okay, and it passes over a light frictionless pulley, meaning the tension on that side should be equal to the tension on this side. Okay, great. Now to another block of mass 2 kg. Okay, now the 2 kg mass hangs vertically as shown in the diagram. Okay, we are happy there. Now further information is given. The 4 kilogram block is now released. Again, once you hear that word, it means the initial velocity was 0. Okay, when we release, there will be a movement of the system. Okay, now, and the system of masses moves to the right. Okay, so we can consider that as the positive direction of motion. And obviously, for the 4 kg block, it moves to the right. That would be to the right. But what would be the movement of the 2 kg block? It would be downward. So also downward would also campaign as a positive, because this is more like moving to the right and down, so to speak. Think about those things. Now the coefficient of kinetic friction, because we are moving, is 4 on the 4 kg block, and the surface of the table is 0.25. Okay. Now this is already suggesting that we will be using this formula. Fk equals mu k times the normal force. And we definitely need the frictional force. So we will use that equation. And of course, ignore the effects of air friction, so that we want to hear as well, because it can interfere. For example, this 2 kg block would be falling down. Now there could be two forces, the gravitational force, it could be the tension, as well as air friction. Can you see? Now we are eliminating air friction so that we know the free body diagram on the 2 kg block is like that. Okay, so that is very important. Nice. State Newton's second law of motion in words. Okay, so of course, guys, to avoid wasting time, I'm not going to define it, but I will just highlight it. It says the resultant force is the product of mass and acceleration. In fact, don't write that. Just say when a resultant force acts on an object, it causes that object to accelerate in the direction of the resultant force. such that the acceleration is directly proportional to the resultant force and inversely proportional to the mass of the object. So if you say this in words, you are good to go. Now, I'm just trying to avoid wasting time writing this one because this is something in the textbooks, so you should be able to get it right. Okay, so that is the story. So it says now draw a free body diagram of all forces acting on the block before motion. Now that could be a problem if you don't pay attention. Before motion, everything was in equilibrium. There was no resultant force in any direction. So that means we need to take care to ensure that the forces acting are of equal magnitudes, at least in one plane. For example, we can say the vertical forces must be of the same magnitude. Right? Right. So meaning those arrows must be of equal lengths, and then we can say the horizontal forces also must be of equal magnitudes. Okay, so this looks like they are like that. So this would be the normal force. This would be the tension on the string. This would be Fg. Sometimes you can write small letter w. So the small letter w represents weight, and then here we can say this is static friction. Fs meaning static friction. So those are the labels that are acceptable, and don't find yourself writing kinetic friction. Remember, we're not moving, and the emphasis here is to make sure these lines are of the same length and those ones are of the same length, because there was no resultant force. So that statement is key. So if you find that this one is longer than the other, you are suggesting that we are moving to the right already. So some questions have a catch in them. So in physics, you need to be obsessed and compelled, okay? Because if you're not obsessed and compelled, you'll lose easy marks, because this is an easy question, but it's technical. You can't just approach it however you want. Okay. Now, calculate the magnitude. So basically, we are focusing on the size, magnitude, of the force acting on the 4 kg block. I mean, the frictional force acting on the 4 kg block. So this is easy. We know that Fk, because now this is moving, because we're saying the frictional force acting. Remember, we're given the kinetic friction, so we were not given the coefficient of static friction. So this is Fk equals mu k times the normal force. But again, do take care to draw the free body diagram. Now remember, friction is influenced by those vertical forces. And what do we know? Those two are equal. So we know that the normal force and the Fg are equal, right? So this means Fk is going to be this 0.25 into, now this one, if this is Fg, which is equal to mg, this one is going to be equal to minus mg. But remember, what are we doing? Magnitude. So the sign is insignificant at this point. We don't care about the sign. So this is going to be the mass, which is the 4 kg block. So this is 4 times 9.8. So therefore, our frictional force is going to be what we get over there. So this is 0.25 into 4 times 9.8. So we get 9.8 newtons. And remember, we were only focusing on the magnitude. Otherwise, if you included direction, you would say to the left, because the kinetic friction would go to the left. All right, So you get a mark for this and specifically for that calculation and the final answer. Remember, the final answer must carry the correct unit. So this is an easy 3 marks, and this is your aid in ensuring that you're doing the right actions there. Okay, now we did not answer the question. We just jumped in. Be very careful of not doing this. So this is 2.3.1, okay? So we've got 2.3.2. Now we need to calculate the speed with which the 2 kg mass strikes the ground. 7 marks. Already multi-step approach here. But now what do we know? We know that the initial velocity here is 0 also, because initially it was 0, then it will start moving. But what displacement is it going to move? 1 meters. So we don't have time, but we have displacement. So this tells us we need this formula. V squared or Vf squared is equal to the initial velocity squared plus 2a delta y. And that means we need the acceleration. And we can, using our Newton's laws of motion. So we start with the 4 kg block. We need simultaneous equations here. So if we move to the right, it means the forces responsible for the motion is going to be Fk, which we found is 9,8. Then the tension, which we don't know, but we don't care because it's common to the two. So we can use it as a means to an end. So this is the 4 kg block. Now we know that the resultant force, according to Newton's second law, is equal to ma. Now we can see the tension is bigger. We add the frictional force to it, but now the frictional force is negative. So this is going to be, okay, maybe let's write it nicely. Is equal to ma. So we then substitute. This implies that tension plus. Now this is going to be negative because it's in the opposite direction to the tension, equals 4a. Okay, so therefore if we make t the subject, we're going to have 4a plus 9,8. That would be equation 1. Nice. And then we say, okay, for the 2 kg block, we've got a force upward, that would be the tension, and we've got its weight downward. And if we're moving downward, it means the weight is greater than the tension. This is the 2 kg block. So we know the resultant force is ma. Now gravitational force is greater than what would be the tension. So we say plus minus what is on the tension there. But now, now I'm trying to think, this can hurt, this can hurt. So if we're not substituting a value, we just write plus, okay? Be careful. So this is plus the tension because this is the summation. Avoid doing the subtraction already. Remember, this is a symbol, so we can't put a sign to a symbol. So this is going to be equal to ma. What is our ma there? Is basically, okay, masipal. So this implies Fg is 2 times 9,8 plus the tension equals 2a. Now we want the tension. Therefore, the tension is going to be equal to 2a minus that one. That is 19,6. 9,8 times 2, it's 19,6. Okay, we make that one equation 2. Now be careful, like I said, what matters is when you're not substituting a value, you can't put a sign. Okay, be careful of that. Don't make a mistake. These mistakes often haunt people. So we can see that essentially this implies, since this is all tension, so it means 4a plus 9,8 must be equal to 4a, what am I doing? 2a minus 19,6. Be very careful. Be very careful. Mistakes can occur here. Then what do? We transpose this one to this side or that one to the other side. But now I'm trying to think. It looks like we are running into some situation. It looks like we're running into some situation. Why is it doing it? I'm seeing a problem now. You know, I'm noticing a problem. But this is a non-issue, but we'll see. This becomes, if we transpose this to the other side, we get 2a, ne? We get 2a. So this is 2a equals, so move on. 2a equals, this is 19,6, and then we add that. So we're going to say minus 9,8. We get 9,8. Mark, 19,6 plus 9,8. This is 29,4. Okay, but now remember this is negative here. So therefore our A is going to be equal to. Now this one doesn't make sense, isn't it? Yeah. 29,8,4 divided by 2 gives us 14,7. I can't. It's even worse. It's minus 14,7. We have a problem. Renale bothata. Right? Renale bothata. Because we can't get a negative acceleration. Remember, the acceleration is in the positive direction, so it has to be positive. So I do think our own creation has hurt us, eh? Even though this is a symbol, now it means we have to do it, eh? Because it's in the opposite direction. But sometimes this is not supposed to be the case, though. It's not supposed to be the case. But anyway. It's all right. So that is what this means. This is what this means. So maybe let's adjust it here. But sometimes I don't know why it does this. But then it says the question is not well designed. Or maybe I'm crazy. Maybe let's leave it at that fact that I'm probably crazy. Because it's easy to not do things right here. So maybe here we need a plus. Then we need a plus. Now it changes everything, eh? Everything changes. So this means this one would be minus 2a. Because we'll transpose it to that side while we transpose the tension. So this would be minus 2a. Yeah. Okay. Now this one becomes 6a equals, now 19,6 minus 9,8 is just going to be 9,8. Now let's see, 9,8 divided by 6. It gives us 1,633 meters per second down. Now that makes sense because it's positive. So it means we needed to do some modification. Of course, watch what you're doing, guys, so that whatever you get, it doesn't embarrass you. Okay, we have the acceleration. Some questions are like this. So try to adjust accordingly. You know, it helps. So what are we looking for? The speed. We can say then we know that the final velocity squared equals initial velocity squared plus 2a. This time it's not g, eh? So we write it as such. This implies that our final velocity squared would be 0 squared plus 2 to 1,633 into 1. Remember, we're being displaced downward in the positive direction. So therefore, our final velocity is going to be the square root of 0 squared plus 2 into 1,633 into 1. So let's get it. Square root of basically 2 into 1,633. That's exactly what that is. So we get a velocity of 1,0, no, 1,81 to 2 decimal places meters per second. Of course, we were just doing the speed. Speed is a scalar quantity. No need for including direction. So you can see here that quite a heavy one. 3 steps at best. Yeah, that's it. Okay, how do we mark here? Well, for me, nothing was really out of the ordinary, but that equation was important to get. This equation is important to get, but also that calculation was important. Easy, 3 marks. And then calculation there, 4 marks. Then we can say formula 5, substitution 6, 7 for the answer, but it must carry the correct SI unit. So that is 7 marks. Okay, so a very nice question, guys. All right, folks, so that is essentially those 7 marks. Let's not beat about the bush and we move on. So this is 2.4. Sorry, 2.4 says, explain why the motion of the 2 kg block cannot be categorized as free fall motion. First of all, we can appreciate that the acceleration is not g, right? So we are not accelerating due to gravity, meaning gravitational force is not the only force acting. Again, if you focus on our free body diagram right there for the 2 kg block, you'll appreciate that there's 2 forces, there's tension and there's gravitational force. So there's no gravitational force only. So we've got 2 options here. We can just simply say the gravitational force is not the only force acting on the 2 kg block. Okay, guys, try to answer fully so that no one starts asking questions in their mind. What is the student trying to get to? It's not the only force acting on which block, Yes, the question is clear, but are you really answering the question? Make it clear that you're actually answering the question yourself so that there's no second invitation to this. All right, so guys, this is easy 2 marks. Can you see it's as brief as it can be? Now, this is the nicest question, guys. Please get the marks here. It's usually not so bad. But what is nice, can you see this mirrors some vertical projectile motion together with Newton's laws of motion. Very interesting stuff. And as you can see, look at that question 1.3. Do you see? We did think of a situation when we don't do a free fall. Can't you see this is part of it? Exactly. This is part of it. So think about these things and they will help in making sure that marks are scored whenever that is possible. Obviously, guys, once you finish this question, you may feel a bit boxed, Now, the best strategy would be to jump around. You can jump to momentum. This is usually the easier one. This one can boost your confidence. You come here. You can actually bank a lot of time here because you can answer this at a go without struggling, usually. Yes, some higher grade questions can come from here, but you can just jump here. Do this one, buy some time to come and dance with this one, because usually this one is hot. It's hot like pepper, green pepper. No, not green pepper. So ayidlali. So awufuna ukuthi ugqiba ukubox wayile phinda uzoziboxisa ngaleya. Hayi, it means now ulichanhliziyo. But anyway, I'm gonna carry on systematically. Question 3. Question 3, what does question 3 says? A ball A is thrown vertically upwards. Thrown, meaning it's a projectile. At least. Until we hear some very nice statement, okay? So far, we can think of a projectile vertically downwards from the top of a building, which is 90 meters high. Now, at a velocity of 12 meters per second. Now, at the same instant, a second ball, see, same instant, meaning immediately this one is being thrown. The other one is also doing its own things. A second identical ball. Identical in what nature? We really don't care. B is thrown upwards at a velocity of 30 meters per second. Now, ball A and B pass each other after 2,135 seconds. Now, here's our famous statement. Ignore. Now we know these two objects are projectiles. And this is usually the topic for grade 12s. So, now, folks, I will always choose a direction. For me, I find it easier to choose upward as positive. But sometimes, as you would see, please watch that video from 2005, the physics paper 1. 2005, the higher grade paper. It's not really too bad. You look at it, you will see there that in the VPM, actually direction was forced down on to the student. It can happen, so be familiar with such questions. Very nice stuff, and please do check that video out. I tried to be as comprehensive as possible in there. This can help to revise. Don't worry about certain sections not being in your exam. But those sections emphasize the same point because they still dance around the same topics and concepts that you still get examined on. So don't be fooled by the year in which that paper was written, but focus on the content of that paper and make sure you learn the science. Okay, so now let's go on. So choosing upward is positive, not a problem. That would mean downward is negative, okay? Great. So now this one says, give the direction of the acceleration. See, we want the direction of the acceleration of ball B while moving upward. So since these are projectiles, we know that ball A, free body diagram, maybe let's do it a bit further. Free body diagram of ball A, it's downward. The same for ball B. It's also downward because only gravity is acting there. So if this is gravitational force, it means acceleration is equal to g and it's downward. Same thing. There. So it would be downward. 3.1, we write the direction downward. And make sure you pay attention to the question. Don't be telling us 9,8 meters per second, okay? You will be dead, okay? So 3.2, it says, calculate the velocity of ball B the moment it passes ball A. That's a very easy one. So we know the initial velocity. We don't know the final velocity. That's what we want, but we know the acceleration. So the basic equation, Vf equals Vi plus G delta T, because the acceleration is G here. So this implies that the final velocity is initial. Remember, we chose upward as positive, so this is going to be 30 plus this is downward, it's going to be minus 9,8. So be very careful with the substitutions. So times the time. We're told the time that they passed each other is 2,135. Okay. You can go on and write your shopping list, guys. I'm not really the fan because at grade 12 level, you should be able to know what you are given and be able to use it effectively. So there's no time for spoon feeding per se. Even what I'm doing is spoon feeding at its best right now. Okay. So what are we getting here? We are getting a 9,08 meters per second. And this is upward, but the question said velocity, so we need to include direction. Because upwards. Because direction is important here. Once the question says velocity, that's a vector quantity, meaning we must have the correct unit of measurement, direction, to get the last mark. The value alone is insignificant. So formula, substitutions, and the answer, if those two are correct. If those two are not, you lose the last mark, okay? Remember that. So 3.3. It says now calculate the distance between balls A and B, 2,5 seconds. After the two balls were projected, meaning from the beginning. So this is one of those questions, slightly leaning towards the higher grade because, again, a standard grader would not know how to handle this one. Okay, so now what are we going to do? We need to consider first the ball A, because first of all, ball B may have come from here. Maybe let's say this is the trajectory of ball B. Ball B may have done its own things like that. We don't know. Meaning ball B is probably here. Probably at the turning point. We don't know. Or maybe has turned. We don't know. But this is the possible areas we can think of. But ball A, on the same time, this one is just coming straight down. Ball A may be somewhere there. Right? So ball A may be there, meaning it has not reached the ground. So there may be some height to the ground remaining. So if we want the distance between the two, wherever this is, it could be this distance right here. It could be that distance right there. Or it could be this distance right there. But at the end of the day, it's any one of those distances. Ne? Very interesting stuff. Okay, let's work it out nicely. So what are we going to do? We'll just say, first of all, let's look at ball A. Sometimes separating things becomes the best option. For ball A, we want to know what distance will it have covered. So we can say, well, delta y is equal to initial velocity times delta t plus half g delta t squared, because we're still doing motion under the influence of gravity only. Now remember, we said downward is negative, so this is going to be minus 12 into, now the time is 2,5 seconds. Be careful not to use the other time. So this is minus 9,8 times 2,5 squared. Therefore, delta y is going to be what we see there. So we've got minus 12 into 2,5 plus 0,5 into minus 9,8 into 2,5 squared. Be very careful of your substitutions. They will hurt if you don't do it right. Okay, so this is minus 60,7 625 meters. Now this is literally 60,625 meters down. Okay, can you see it has not covered the full 90? So this means there's this remaining portion here, which is going to be 90 minus this 60,625. And then what do we get? Because we want its position above the ground. That would help us a lot. So we just add the 90 there. It gives us some 29,375 meters above ground. So this is very important, because we know if we use the distance above ground of ball A, it will help us when we combine with the distance above ground of ball B, so that we can just take the difference to get that height. Makes life a lot easier. Okay, now we can say for ball A, so for ball B, what will we see? Perform a similar calculation. Delta y is equal to the initial velocity times time times half g delta t squared. This implies that our delta y is, now upward we chose as positive, so this is 2,5 plus 0,5 into minus 9,8, because that's downward, times 2,5 squared. Therefore our delta y there is, so we've got 30 into 2,5 plus 0,5 into minus 9,8 into 2,5 squared. Alright, so this one is giving us 44,375 meters. Now this is positive, so this is upwards. Oops. Upwards. Okay, nice. Now can you see, guys, this is probably here, because it's probably before it turns, or it could be after it turns, but we really don't care. Let's just assume now that is before it turned. So can you see we have a clear picture now of where ball B is in this moment. So we can remove what is not necessary. So can you see, guys, all we want to calculate now is this distance between these two. So that distance is what we want. So it doesn't really matter how this one is, whether it has turned or not, but what is important is that the distance of B above ground minus the distance of A above ground will give us that distance between them. So we can say here then, the distance between A and B is going to be, what is it? We will take that one of B. It's going to be 44,375 minus, now the distance of A above ground is going to be 90. We need to show that calculation, minus that displacement it took down. This is where most students would get caught. Therefore that distance is going to be, now we're going to say 44 minus into 90 minus 60,625. So it gives us 15 meters. Okay, great. Now distance is a scalar quantity. We don't bother with the direction. So most students will get caught here, because as much as we did it there in our sketch, we need to show this calculation. It's important. Alright, so how do we score marks here? Well, for ball A, first of all, I would say this is good. For ball B, that is good. Now, that is 2 marks. And of course, one of the formulae, 3 marks. Now this is a calculation. That's the 4th mark. That's the 5th mark. Okay, great stuff. So that's nice. That's what we do. Okay, I hope that is clear. So let's just finish off this question nicely. So 3.4. Now we need to do, on the same set of axes, we need to draw the position time graphs of the motion of balls A and B. Okay, what are the constraints? Ball A, from the moment it was projected until it reaches the ground. Okay, ball B, from the moment it was projected until it passes ball A. Okay, that's the limit. And then we need to clearly indicate the time at which the two balls pass each other. Okay, nice. And then we need to use ground zero. I don't know why something is not right here. We need to use ground zero as, the ground is 0 position. Okay, and then of course we label the graphs, not a problem. Easy stuff. So first of all, we need to give a topic. This is the position time graphs of A and B. Okay, it must have a topic. And then of course we do our axis. Remember position, if we're taking ground as 0 reference point, so this is suggesting that, okay, we are going only to the ground, so that means first quadrant only. So this would be time in seconds. Okay, this is going to be position in meters. How do we write meters? Meters. Nice. So that is the story and that's the origin. Okay, need to be clear about that. So ball A started from 90 and then it hit the ground. Okay, so that would be 90 meters. But B caught up to A there. And what is the time there when they catch up? Basically, lubangubani go 2,135 seconds, and that's all we needed to show. So, of course, this is ball A, that is ball B. Now, this is, of course, we need to explain here that taking up as positive indicate this thing. It may look not so important, but it's important. And then, of course, if you're taking up as negative, this would be inverted. Okay, this would be inverted. Nice. So let's leave it at that and not complicate it. So we get 1 mark for the shape of A, shape of B, and then the time at which these two met. And of course the rest of the thing, the extra mark could be for the rest of the business. So VPM is not so bad sometimes. Sometimes it's horrible. So it will depend on the mood of the examiner at the time. So this could be some nice 12 marks when the questions are not so hectic. But they can be quite hectic, okay? Be very careful. So you will find this memorandum attached to this question paper in the description below if you're interested in it. All right. Let's move on to the next question. Now, this is the one that could give you some relief if you feel like question 1 boxed you. Do this first and then you go back to question 3. Just to keep gaining some strength, some confidence, and some relief of the pain, you know. Sometimes it gets very hectic, okay? Let's quickly do this. A delivery vehicle mass 5,000 kgs is moving at a constant velocity. No. Moving at a velocity of 15 meters per second to the right, so we can choose to the right as positive. Collides head-on with a car of mass 2,000 kgs, moving at 20 meters per second in the opposite direction. Okay, that would be negative. Ne? Immediately after the collision, the car moves at a velocity After collision, the car moves at a velocity of 15 meters per second to the right. So can you see it has changed its direction of motion? Now, conservation of linear momentum is always there, okay? So these are a guarantee of marks there. Write down the principle of conservation of linear momentum in words. Well, we know that the total linear momentum in an isolated system is conserved, or sometimes you can say constant, or remains constant, whatever. You choose the words, but make sure the story of total can't be just any, but total and linear momentum. And we must hear the word isolated system or closed system. Those are the two main ones, because the conservation already is suggestive of consistency. So there's not so much there. So those are the 2 marks in there. Okay. 4.2 says, calculate the magnitude of the velocity. See, magnitude. We're not going to worry about direction. Of the delivery vehicle immediately after the collision. So we know that P before must be equal to P after. Ne? Now, this is going to be the mass of the truck multiplied by the velocity of the truck. Can you see? 2 subscripts at a go is ridiculous. I hate this notation. Anyway, hating it or not doesn't really matter. It is what you have to deal with times the initial velocity of the car equals the mass of the truck times the final velocity of the truck plus the mass of the car times the final velocity of the car. Okay, now the mass of the truck is 5 squadro into the initial velocity. It was 15, positive because it's in the right direction. So this one was 2 squadro into, now this one is going to be minus 20 because that was in the opposite direction. So this is 5,000 times the final velocity of the truck, which is what we want, plus 2,000 into, this time it moved at 5 into the right, so it's positive. Okay, now I can just move this quickly and say now the final velocity of the truck is going to be this right hand side, 5,000 into 15 plus 2,000 into minus 20. Then we minus this one when we transpose 2,000 into 5. All of this is divided by 5,000. Okay, just to make it easy to get to the answer without sweating. I'm feeling dizzy, guys. You know, I have sinuses. I'm not well at all. I'm feeling a lot dizzy. I don't know if I'm going to keep up with this memo, but unfortunately I made the promise that I will do this and give you some MCQ experience there, and then on top of it all, you know, of course do some revision with you guys. So I'm tired of also sleeping in my bed, so it's killing me. So what am I getting here? 5 meters per second. Remember, the question was, what is the magnitude? So we don't worry about the direction. But if direction was important, remember this came out as positive. So you can even indicate that it is going to be to the right as well. But if you put it in brackets, it's safer than you leave it there. Either way, they mark the first thing you wrote. Now, we get a mark for this, right? We get a mark for the left-hand side. We get a mark for the right-hand side. So that is 3 marks already. Then we get a mark for the answer. So easy 4 marks, not complicated. So 4.3. Now we are told here, if the collision lasts for 0.4 seconds, there will always be a question on impulse, guys, okay? Calculate the force the delivery vehicle exerts on the car. So that means this affects the car. So we can draw a free body diagram of the car and say the force applied to it to the right is going to be the force of track on car. That is what we are dealing with. All right, okay, all right. So the best object to use is the car, right? Right, because the force is applied on the car. So we can say F delta T equals the change of momentum for that object. Of course, we know that the free body diagram is this one. This is the force of track on car. Okay, so this would be the force we're looking for times 0,4 equals the change in momentum is the mass of the car, which is 2000, into the change of momentum is going to be the final velocity, it was 5, minus the initial velocity was what? Minus 20. Be very careful of signs. Therefore, our F is going to be equal to 2000 into 5 plus 20, all divided by 0,4. Let's see what that is. So 2000 into 25 divided by 0,4. So we get 125,000 newtons. Again, what was the question? The force. Remember, this came out positive. It is to the right. But again, what was the direction given? Moving to the right. Yes, we can write to the right. To the right. Because force is a vector. And there was no mention of magnitude. So if we don't write the direction for vectors, you are applying for some serious death. Okay? Substitutions. Answer with the unit and the direction for marks. Okay? Not a big deal. Not a big deal. Okay? But someone may say correct substitutions, but this change in momentum is a calculation on its own. One can say, maybe since that is a calculation, the change in momentum, that could also be the mark there. But if your answer misses the direction, if it misses the direction and it misses the correct unit, then you lose the last mark, okay? Otherwise, as you can see, usually this section is a breather. The headache, guys, I have, and the dizziness I'm feeling is killing me. Paper 1 is also longish, It's boring. Okay, let's do question 5 as fast as we can. Now, question 5 says a boy on a roller skates moves at a constant velocity in an easterly direction along a frictionless horizontal AB track carrying a parcel. Okay, he decides to increase his velocity by throwing the parcel horizontally away from him. Now, what comes to mind, guys? If he throws the parcel, in which direction must he do it if he wants to increase the speed? He needs to throw it backward, right? Because Newton's 3 is going to say the force that he applies on the parcel to throw it that way is going to be the force the parcel will apply on him. Remember, he's already moving. There's no friction. That will add more force to his already existing force. And therefore, we will increase the resultant force and increase his speed by accelerating in that direction. So can you see Newton's third law of action and reaction? Can you see in the MCQs we came across this? It's coming back now. It's being applied here. And this is also marrying momentum together with Newton's third law, which usually applies there, and the work energy theorem, because I mean this is where we are right now. Okay, so that is the story. Then we've got everything given to us. So let's answer some questions. It says, in which direction must the parcel be thrown to cause a maximum increase in the velocity? So if we are moving in the easterly direction, it must be in the westerly direction, the opposite direction. We must throw it in the westerly direction. So easy one mark. Can you see these questions seek understanding rather than reproducing what you have studied in your textbook per se. Now name and define. Can you see name and then define in words the law of physics that was applied in question 5.1. What is that? Can you see, guys? See, it's coming back. We saw it in the MCQs. Now it's coming back in a bit more detail. So this is Newton third law. You can write Newton 3. And then what does it state? Is that body A, or maybe let's say when body A exerts a force on body B, body B, not Bobby, but body B, will exert an equal but oppositely directed force on body A. Okay, so that is the story. Of course, there's many ways of phrasing these things. You can cram whatever you have, but if you don't remember, this is the essence of the science. It's an action-reaction pair, basically. Nice and easy. So you get a mark for stating the law, and then you get 2 marks for the definition usually. Okay, so that would be 3 marks in total. Nice and easy. So 5.3 says, now we have a story. He reaches point B at a velocity of 6 meters per second. Can you see it definitely did increase, and continues to move up a rough section. So that means we're going to have kinetic friction because he's moving. Can you see it's shown with dotted lines there? BC off the track and comes to rest, meaning he stops at position X. So that means the final velocity at X is 0. That's the main thing. Which is also 4 meters above the ground as shown in the diagram below. Now a constant frictional force of 40 newtons acts on the roller skates. The combined mass of the boy and the roller skates is 75 kgs. Okay, no, 57 kgs. All right. So we are supposed to calculate the value of theta, the inclined plane. Okay, again, it's one of those questions where no standard grade can handle this. Only higher graders, because usually you need to perform some simultaneous equations of some sort. All right. So how do we plan what we need to do here? Of course, no one said how we're going to do it. We're just asked to do it. So what are we going to do? Well, if we look at this situation right here, we basically need the incline, right? We need the incline. Basically, delta x is not known, because if we can find the incline there, that would be the hypotenuse side, because this is at 90 degrees right here with the horizontal. So we've got a right angled triangle, so we can define sine theta as the opposite of a hypotenuse. Then we need that first. So can you see 2 steps? So now we need to use our knowledge, what we have. So now, what formula can help us? Now we can think of 2 formulas. Sometimes we're just planning how we're going to do it. We say W net is equal to the change in kinetic energy. Okay, we can get the change in kinetic energy, but this means we have the resultant force times delta x cos of theta equals change in kinetic energy. Of course, we can write it this way: half m into final velocity squared minus initial velocity squared. But now we've got a problem. We don't have the resultant force. We also don't have delta x. So this means if we use this formula, we're going to need another one so that we can solve for the unknown, or at least represent maybe this resultant force twice so that we can use it to get to delta x. Okay, so that is the idea it gives us. Why do we not know? If we draw the free body diagram on our skates, right, when it is moving up the incline, now I'm going to assume to the west is down the incline. We've got friction. This is Fk. And we've got Fg parallel, which will be down the plane. This is equal to mg sine theta. Now we don't know the angle because sine theta is that of the elevation. We don't know it. That means we are not able to calculate Fg parallel. And we cannot get the resultant force as a result. Can you see? This is why this is a question mark. We are not able to do it looking at our stories there. So this is not the best formula to use. But we also know this one. Work done by the non-conservative force is equal to the change in the potential energy, plus the change in kinetic energy. Okay, now what do we know? The non-conservative force here is the friction. So we have its value, it's given. And therefore we can work out the displacement nicely from here, because this formula would suggest that we've got Fk times delta x times cos theta. But this theta is not the angle of inclination, be careful of that. Equals, that's why sometimes I don't like this using the same variable that sometimes is used commonly. There has to be a change of standard so that we don't end up with confusions. Either way, guys, hey, if you can't defeat them, you join them. So mg is the common one, but the height, the difference in the heights from the initial to the final is the most important to suggest a change in our potential energy. Now this one is half m as well. Final velocity squared minus initial velocity squared would give us this one. Can you see? We know all of these things except delta x, and that's what we saw we need. Okay, so let's move on. This is 40. You just put it as it is, times delta x. Now cos of theta is going to be cos of, now remember friction is doing opposite work to the displacement, so that would be 180 degrees equals, now mg is what? 57, okay, times 9,8. Now into, this is 4 minus 0 plus 0,5 into 57 into, now this is 0 squared. Okay, maybe this one we need to be very careful on how we do this. So this is going to be 0 squared minus into 6 squared. So we need to be very cautious here. Square brackets are the safest. This is 0. Okay, good. So now we can clean up everything. This is basically going to be minus 40 delta x equals, so let's clean up the right hand side. So we've got 57 into 9,8 into 4 basically, plus 0,5 into 57 into minus into 6 all squared. Be very careful again with brackets here. It can be very dangerous if you don't do the things properly. Ne? So I'm getting here a 1208,4. Okay, so therefore our delta x is going to give us a negative answer because we'll divide by negative 40. Some answers do not come out as perfect as you wish. As you can see, this is minus 30,21. Now, this is meters. But remember, friction was doing opposite work because it's going that way. So it's going to read the displacement in reverse. This is as good as just 30,21 meters. Ne? That's very key. Okay, move on. So, okay, now that we have the hypotenuse, we can answer the question. Then, sine theta is going to be opposite 4 meters over hypotenuse, which is 30,21. Therefore, our theta is going to be arc sine of 4 divided by 30,21. All right. And what is our theta? So we go shift sine 4 divided by 30,21. We close it. It gives us to 2 decimal places. This is 7,61 degrees. Okay, we can accept that. It's not quite a big angle there. Nice. So you can see, guys, some questions here are basically labor intensive, like this one. It's too many calculations to handle. So try to make sure you use your calculator effectively here to simplify yourself, because too many simplifications one by one, you will end up with a mistake. But even though you can do this combined, also make sure you know how to use the calculator effectively. Okay, so we can appreciate that the free body diagram played a crucial role, right, in making us understand the best approach. And this one did not quite tie up well, while the second one tied up well. Okay, sometimes trial and error, you have to dance with the two. That is why questions like this, you don't just answer straight up. You first try it on your rough work and then put down what you see is the best approach you can use. Now, obviously, formulae important. Nice. And then we can say here, well, this right-hand side is complex. So we can just say the right-hand side is a mark, the left-hand side is a mark, okay? We get 3 marks. Finding delta x is the 4th mark, okay? And then the angle. Remember, this is maths applied. It's not a formula in physics, so we're not going to care about that. So that is how we score those 5 marks. Nice and easy. Okay, we move on to 5.4. All right. Great. Now 5.4 says, a remote controlled car of mass 4 kgs is driven up an inclined plane which makes an angle of 30 degrees with the horizontal by an average forward force of 80 newtons as shown in the diagram. Okay, so this is the force applied, it's not the resultant force. Great. Now it says the car experiences a constant. The car experiences a constant frictional force of 15 newtons as it moves up the inclined plane. Okay, good. Now the speed of the car at the bottom of the inclined plane is 3 meters per second. Okay, that's what we have. Now the question says use energy principles. That means no equations of motion. Should you find yourself using equations of motion, you are losing those marks, irrespective of how correct the answer is going to come out to be. To calculate the speed is a scalar quantity, so we don't worry about its direction of the car after it has traveled 5 meters up the incline. So this means from here, maybe, up till there. So that would be 5 meters, okay? Now, obviously from 3, this must have increased to more than 3. So we expect a final velocity that would be higher than what we have there. Now remember, in this question 5, the work energy theorem must be applied somehow. Since we didn't use it here, then it will come back both, because this is the one. Sometimes in this one has to state the work energy theorem, but sometimes you can see when you integrate, you can even provide room to ask a different law in this question. All right. So now this one should work because we will have a free body diagram. Again, I'm going to assume to the right, this is up the incline, okay? So I can say this is 18 newtons. And we will have two forces opposing that. It's going to be Fk as well as Fg parallel. Now to the west is going to be down the slope. Okay. So if we're still moving up, it means we have a resultant force in the direction. So if we've got a resultant force, it means we are accelerating. And if we're accelerating, we expect to increase our velocity. Okay, good. So the work energy theorem tells us that W net is equal to the change in the kinetic energy of the object. Now what does this imply? It means the resultant force multiplied by the displacement times the cos of theta should be equal to half m. Change in kinetic energy, we can just say this is the final velocity squared minus initial velocity squared. Now we can substitute. The resultant force is going to be Fg parallel plus Fk plus that. So this is as good as saying 80 plus into minus, because these ones are negative now, it's going to be 4 times 9,8 minus, 4 times 9,8 sine 30 degrees minus the frictional force, which is 15. Okay, so be careful of the signs. They can horrify somebody. Remember, this gives us the resultant force, so we need to group it nicely. And then we're multiplying the displacement as well as the cos of an angle. Now the cos of the angle, remember, this is being displaced upward, so the angle between displacement and motion is 0. So this is 0 degrees, okay? Equals half of 4 into the final velocity squared minus the initial velocity squared. Okay, that's what we have. So it's getting a bit longer. Now we can clean up the right hand side. So we've got 80 minus, in fact, minus into. We can factor out that negative and add the 2 inside. It's going to be 4 times 9,8 times 0,5, because cos theta is 0,5 from special angles, and then we add 15 there. Then we close the bracket and then we multiply that by 5. Okay, cos of 0 is 1, so we leave that one as it is. So what do we get? We get 227 equals. Now we clean up the right hand side. The right hand side is basically going to be this should not be there. This should be 3. Okay. I'm making a mess. So now half of 4 is 2. 2 times the final velocity is going to be 2 times the final velocity squared minus, this one is going to be minus 9. Minus 9 times 2 is going to be minus 18. Okay, that's what we have. So therefore our final velocity is going to be equal to the square root. Now we transpose that there. This is 227 plus 18 then we divide that by 2, and then we take the square root. Easy stuff. So square root of 227 plus 18 divided by 2. What do we get? We get 11, 0.07 meters per second. Again, we just wanted the velocity. We didn't want the, we wanted the speed. Speed is a scalar quantity. We don't worry about direction. All right. All right, folks, this is how easy this looks. So we get a mark for our formula. Now remember, this whole calculation, this is a calculation first of all, and the entire left hand side, is a mark. So 2 marks for that. And then this entire right hand side, that's again 4 marks there. And then we can say the general substitutions, it's a mark in the final answer. So this is how these 6 marks are scored. It's quite intense, eh? It's quite intense. In one step, we killed a lot of birds with just 1 stone. So this could be the marks that you get. But remember, guys, your absolution is definitely going to be knowing the free body diagram of the forces influencing the motion. Nice. So this is now the end of the mechanics section, right? This is where the most marks stay. Sorry for the noise, guys. We've got a helicopter here. So, and also there's an airport not so far from here. So some planes pass by here. So there can be a lot of noise. Of course, guys, you will find this memo of mine together with this question paper in the description if you'll be interested in it. All right, so now let's see. We're going to do the Doppler effect. Let's do the Doppler effect stuff. Nice. So question 6, let's start it on a new page. All right. Now, this is usually easy. Now, a siren of a stationary fire truck emits sound waves with a frequency of 1800 Hertz. And then we're told a car traveling on a straight line horizontal road at a constant speed of 30 meters per second passes the fire truck and continues in the same constant speed. Okay? Now, remember, who's the source? Is the siren, but it's stationary. But the listener is going to be the person in the car, and that one is moving towards the truck and then passes the truck. And then we know on approach, this person on the car will hear a higher frequency. But when leaving the truck, the person will hear a decreasing frequency, because that's what the Doppler effect says. Now, obviously, guys, these are the easy marks. State the Doppler effect in words. Basically, this is an apparent change in frequency as observed by a listener from a source of the sound when the two move relative to each other. Okay, so you can just say that in nice English if you know how, but I don't really know. You can just say it's the apparent change. The apparent, it's not exactly true. The apparent change of frequency, okay, observed by the listener when the source and listener move relative to each other. Okay, good. It uses the concept of relative velocity. We used to be asked that question on equations of motion section, relative velocity and stuff, but now here it's better applied in Doppler effect. Of course, guys, say the way you know how, cram it if you have to, but I don't advise cramming. It's a means to an end for sure, but what's the use of advancing forward when you are not so strong? Because it will give us the false impression that you have the right knowledge and the right skill, and then you go and fail us when it matters the most. We give you a job, you mess it up. And this is what we're experiencing in this country, isn't it? All these government institutions that actually are supposed to run the country and maintain the country in good condition, they're failing because the wrong individuals who have the qualifications but not the knowledge, not the skill, you see, not the flexibility, are in charge. And therefore, they make mistakes when it matters the most. And yet, we should be doing less of those and more of the success. And again, when crises hit us, we need people who can come up with quick solutions because they understand how to tweak these. This is when you marry theory and practice, because theory gives you options to modify practice, isn't it? But now if you don't have these together, you're already a disaster, because you will wait until somebody else tells you how to do it. And this is when doors to pests like those propagandas of capitalisms and stuff will get in, because when these ones get stuck, they open doors for those people to manipulate the system in their own favor. And we end up in a mess that we see ourselves in. So please, folks, don't just cram and move forward and give us the impression that you know. For me, it's like a doctor who uses past exam question papers during medical school. That one is likely to make a bad doctor, believe me. So this thing is good, but it can be bad, okay? But at the same time, that still same technique can produce a very excellent doctor, provided that doctor actually studies first and understands the work. Then, to maximize on getting the best marks, uses the question papers as a means to an end, as in to just achieve the best marks. But the knowledge is already internalized, it's already understood, it's already captured and can be applied. So you see, this is to say, yes, do use these past exam question papers, but don't just use them to pass, okay? If you're just using them to pass, to get to cross the line, then you're not learning, okay? You're not learning at all. You're just improvising. And you will be useless even after passing. That's the problem. But if you study first, you understand your work, and you become strong, you become flexible, you can apply your knowledge when you need to. Obviously, to now make up the dean's recommended candidate, you need to have an excellent mark. So you can use your past exam question papers to maneuver to that level, because guess what? It's purely for the awards. Because what does it matter anyway? It doesn't matter at all. Well, I mean, getting distinctions and cum laudes in varsity doesn't really change the person you become as a professional, isn't it? It just gives us the impression that you're good. And you better be, because we'll give you tasks that require the best. And you fail, we will ridicule you, you will go into depression, and you will feel the world is against you. You'll be going around saying, people don't like me at work, they're making my life difficult, because you gave us the impression you're strong. Remember, we'll always test you. One way or the other, we will test you. If we don't test you ourselves, the situations in your life are going to test you. So be very representative of what you show us as. If you show up as a good individual who's strong and who's charismatic, please be that which you show us. Don't fake it, because some tools can actually give the wrong impression. And we believe you. and then you fail us, and then we get disappointed, and then you cannot survive the change of how we look at you. But remember, our perception of you must be, even when you fall, we need to say, this is a great individual. If he falls, it means anyone would fall. Okay? We need to be at that level where we even are eager to even extend a hand to assist you to rise up again, because we know you are good enough. But if you just fall and you drop into the ground like you're falling off a cliff, we realize that there was nothing here. And we just go on and look and peep and be like, oh, shame, poor thing. We move on. We don't even give you a hand, okay? Be very careful, guys. Certain techniques, yes, they are well preached. But remember, this is what shapes the professional you become tomorrow. So if you just cut the corners and you take the easy way out, yes, you will get out easily, but you will get stuck heavily in the long run. So don't allow that to happen to you. Ne? Yeah, be very careful. It's like money. Money can buy you joy, but money can dip you into trouble if you're not careful with it, okay? Be very careful. Anyway, folks, let us continue with our topic and stop talking nonsense here. Alright, guys, so I needed to take a break. I'm tired, guys. I was feeling dizzy, so I had to take a moment and eat something as well. Okay, let's continue. 6.2 says, how does the pitch of the siren heard by the driver of the car change when the car is moving? Now state only increase, decrease, or remain the same towards the fire engine. Okay, so 6.2.1. Obviously, when this car is moving towards, the pitch is going to increase. Okay, 6.2.2. When it's moving away, it decreases, or maybe let's just write decrease. Easy. So those are easy 2 marks there. So 6.3. Now this is the action. This is the action, but it's usually not too bad. Calculate the frequency detected by the driver of the car as the car moves towards the, remember, towards the fire truck. And then we are told to take the speed of air as 330 meters per second. Okay, so this is going to use the Doppler effect, right? Frequency of listener is going to be V plus or minus the V of the listener, and this is over V plus Vs of the source times the frequency of the source. Okay, so this is what we need to write, okay? This implies, now what are we looking for? The frequency detected by the driver. So this is the frequency of the listener. Equals, now this is 330. Now remember, when we're moving towards, what happens to the numerator? What happens to the numerator is that we subtract. We subtract. So what are we going to subtract? 30, because we want this to be as small as possible. So we're going to subtract 30, because that's the velocity of the listener there, divided by, this is 330. This time the source is stationary, so that would be 0. Now remember, from 330, if we take away this, we end up with a proper fraction, isn't it? Now, a proper fraction is going to do what? It's going to make it less. Mark. It right. Now we have to add, guys. Sorry. I'm losing my focus. We need a proper fraction, because if it is an improper fraction, because if it becomes a proper fraction, we end up in trouble. Yes. So usually this would be 0, but at some point to substitute here is a bit of a scam, you know. The best thing would have been to subtract, but in fact, don't even bother. Just leave it like this, because it's nothing. Nothing is nothing. It cannot change. Even if you write it, you can't be writing nothing there. So on the top, guys, we're going to add, and then we're multiplying this to the frequency emitted, which was 1800 hertz. Okay. Hey, when kutheni nemax ezininzi nje? Anyway, therefore the frequency of the listener is going to be I think this is easy though. So this is going to be, okay, let's first do this. It's going to be 330 plus 30 over 330 into 1800. Of course, if we don't see a higher frequency, then we're in trouble. It is indeed higher. This is 1.9. So this is 1963, comma, to 2 decimal places. It's going to be 64 hertz. My throat, guys, is killing me here. Forgive me for it. So this is 1 mark here. Now substituting this plus 30 is also a mark here. And then knowing that there's nothing here, that's a mark. And the rest of the general substitutions, you see? Final answer. And of course, it must have the correct unit. So that's how we score ourselves those 5 marks. So it's not a big question. So usually the marks here don't really reflect how bad this is, okay, at times. So that is fairly easy. Now 6.4 says sketch the graph. Sketch a graph to show the frequency of the siren changes as a function of time as the driver approaches and then passes the fire truck. No numerical values required, okay? So we're doing a graph to show the frequency. Okay, guys, we're going to write in full. I'm writing in short. The graph of change of frequency as a function of time. I'm just doing it in short, but do it in full, okay? Make sure there's a proper heading. All right, okay, all right. So, so we're going to have time in seconds, and then we're going to have frequency in hertz, okay? Don't be careless. This is important. Of course, when it is coming, it's going to be looking like higher, and then it will drop eventually. It says no numerical values are necessary. Okay. And essentially it goes on like that too. So that's what we would have. So I suppose that would be the mark for this, and then for the rest of it, wow, so nice, 3 marks. Ne? So yo, this canvas must be so silent. Let us change over. We must change over, isn't it? Is it change over? Is it change over? Okay, let's do 6.5 here. It's just 1 mark. It says name the medical instrument that makes use of Doppler effect. It's an ultrasound Doppler. Doppler machine. Okay, so the ultrasound Doppler is actually the one, because this is what we use to measure the velocities of blood within blood vessels in different territories. And it is very useful for neurosurgeons, cardiologists, vascular surgeons, because, for example, a vascular surgeon is trying to do a bypass from the thigh to the lower leg because of atherosclerosis, with men and they're smoking, and women are also following into the poison. Anyway, so when you do a bypass, what you want to know is to measure the flow in a particular vessel after the bypass and see if the velocities are what matches the normal variance. Then that would be adequate perfusion for the tissues in the leg and below. Okay, so an ultrasound Doppler is very helpful, because if those velocities are low, it means there's a kink in the lumen of our construction or the construct, so we need to redo it and make the neck maybe or the opening a bit wider. But sometimes when the velocities are too high as well, it means we made a bigger hole, so we need to actually narrow it to normal values, because if we overload with fluid, what happens? Edema will take place, and edema will kink the blood vessels that are small at the tissue level and cause hypoxia despite an adequate flow. And again, that can worsen the situation. All right, so that is the idea. So an ultrasound Doppler is very useful. So also brain surgeons, someone gets hit by a stroke, but within hours, maybe within 3 hours to 6 hours, but certainly less than 8 hours, they will spot on the CT scan or CT angio that, hey, there is a blockage perhaps in the main branch of the middle cerebral artery. Now, if you want to perfuse the distal areas that are fed by that vessel, because it feeds a large part of the convexity of the brain. Now, you can decide to take the superficial temporal artery in front of your ear there, take one of the branches, create a bare hole in the skull, then you dissect the arachnoid, you get to that level where the vessel is blocked, and then you try, maybe past the blockage, you just try to reanastomose this external carotid artery branch, and that then perfuses the distal areas from the blockage, and that can actually offset the stroke symptoms if you act within reasonable time. Right, and of course we use Dopplers as well. Sometimes we can use a cranial Doppler using the eye as the window into that. We can actually measure the velocities if we don't have a scan. If you have a Doppler, you can just put it, it will tell you exactly where the flow is poor, where the flow is good. So this can be very helpful in diagnosing vascular lesions or vascular malformation lesions like arteriovenous fistulas, and sometimes you can get arteriovenous malformations. Those ones are high flow lesions. So you will see an abnormal flow in a particular vessel, and that already suggests there's either some extra fluid there, and usually it's a connection between an artery and a vein, whether it's normal or abnormal. Whether it's congenital or acquired. Remember, stabs as well can lead to that issue and many other issues. So this instrument is very, very, very useful. But the key thing about it is that it is operator dependent. You need to be proficient in using it. You can't just plug it there and you will know how to use it effectively. So the results can be quite bad if they're used. I mean, if it has been done by a bad individual in the technique. So that's good. Also, some people can use this to measure the blood flow in the placenta, okay, in the placental vessels, to check if the baby is getting adequate blood, especially in mothers with connective tissue disorders, where you know that blood vessels have a tendency to kink and the baby might not be getting enough blood, especially when you measure the estimated weight of that fetus. You realize that it's smaller than the age of the fetus, or the gestational age we say, meaning the duration of the pregnancy. Now you may see that I'm suspecting there might be some issues here. Do we have poor flow into the baby, meaning the baby is going to be small in size, meaning it's going to be intrauterine retardation of growth of that fetus. So you can use the Doppler to measure the flow in the umbilical arteries or in the placenta or placental vessels, and this can give us an indication of what is going on in there. All right. Okay, all right. So that is very, very, very useful. An instrument. So you need to know about it, unfortunately. Even though you probably don't know the details. Now I'm giving you the details. Now you know. All right. Great. So actually, guys, I tried to make a video here when I was doing this revision with my students. Obviously, we stopped at this question here. But now I realized the thing was not recording the screen properly. So I was using the Google Meet, so I don't know, I got stuck here. Sometimes you see this technological deficiency in me is a problem, because you could have enjoyed how my students interact, and you would see the thinking behind the plans to just appreciate, you know, once the technique is well drilled, they will have an idea of what to do, because you would be impressed by how good they respond to this and exactly what is their plan in answering the question, which can also highlight the fact that you also need to adopt a similar approach, because it can help you greatly. In fact, I was impressed as well, because I was happy to see that my guys are on fire, and I hope all of you, even if you are new to this channel, you will be on fire as a result. Anyway, that would be the nice 13 marks. Usually this one is 3 marks, guys. No matter how it is made, it's usually 3 marks, okay? Yeah. Challenges can be posed on the calculation usually, but even there, I promise you, those challenges are not really out of reach, mostly, because it's not too bad, okay? Now let's get to question 8. Sive ukuba sikhiphani lapha. 10 question 8, question 7. Yabona. Funa ukusilahlekisa. Now it says there's 3 small identical metal spheres. Well, we don't know in what regard. I hate that word. But in physics, it's always thrown loosely. Be very careful of what that means, okay? Make sure you read this properly so that you can understand. Now it says 3 small identical metal spheres, K, M, and G, are placed in a vacuum. So what does that mean? Sometimes they would use the word insulated. Now, this is just to suggest that this is a closed system, to suggest that there will be conservation of charge. Right? Right. So that says the law of conservation of charge is at play here. Now it says each sphere carries a charge of 6 nanocoulombs. Now, no one tells us whether this is positive or negative. We're only given magnitude. Now the spheres are arranged such that K and G are each x millimeters from M, as shown in the diagram, okay, meaning they are equidistant. Okay, all right, okay. Now, is that 6 positive? Well, if we see it, it's written like that, but for me that is magnitude, but no one commented about actually the the quality. But since there's nothing that seems different here, we will then assume, I hate questions like this, the way we have to assume that the charges are positive, because that is simply just magnitude. But again, to get an idea of whether this is indeed a positive or a negative, we need to look at the questions. If there's no mention of what charge or what quality of charge is K or G or something like that, provided there's some extra information about some resultant force at M and stuff like that, then we will assume that, okay, most likely this is just a plus 6 nanocoulombs. Now this is suggesting that this is 6 times 10 to the minus 9 coulombs. 6 times 10 to the minus 9 coulombs. That's what nanocoulombs means. Okay. Now it says state Coulomb's law. Easy marks. Ne? Of course, guys, I'm not going to define this one at this point, but we know that the electrostatic force, the electrostatic force is equal to the constant multiplied by the product of charges 1 and 2, all divided by the square of the distance between them. Of course, this is more like Newton's second law, but then you say this in words. So use the formula to remind yourself. But now there's two proportionalities. We know that the electrostatic force is proportional, directly proportional to the product of the charges, but it is inversely proportional to the square of the distance. I don't know what I'm writing there. Hey, sometimes. Okay, so you say all of these things in words. Basically, you write that statement in words, and you mention these proportionalities essentially, and you would score yourself easy 2 marks, because the essence here is on the proportionalities, because it provides us the mathematical relationships. All right, so 7.2. Now we know that the magnitude of the net force exerted on M by K and G is this one. Can you see? We are given the resultant force. Now we're supposed to calculate the distance x between G and M. So can you see there's nothing that seems like there's a trick between these being positive or negative, and essentially if they are given positive, then we can assume that these are positive charges. And that explains this identical nature, perhaps. All right? But be careful, be careful. Don't always assume things, but come to a conclusion, provided there's nothing else that seems to be a bit fishy there. Because if it smells like a rat, it means there's a rat in the kitchen, right? Right. So easy 8 marks. So again, simultaneous equations. Usually this is the big question in electrostatics. And obviously, guys, this inclines in the direction of the higher order type question. So let's sort it out. Now, of course, we will look at the electrostatic force between those two and between those two. But now here's the thing. What is the charge on M? Obviously, we're told these are the same, so this should be plus 6 times 10 to the minus 9 coulombs as well. So we know that, well, the force is acting on Q. It's going to be in that direction and in this direction. So obviously, using the parallelogram method, we will know that the resultant force is going to be in this direction, right? And then, of course, when we shift these forces a bit, like that, because it's not 100% now, it's embarrassing me. It means as linganis. So so we will know that this would mark our resultant force. Okay, so that would be the resultant force, R. Nice. So we are being told what this would be. So in any case, we can shift this force to here, so that we have a right-angled triangle, because remember, between these two forces there was a 90 degrees, so it can show up there. So we can use this triangle to deal with our problems. Okay, all right, okay. So if we use that triangle, this is easy because we know that this would still be x millimeters. So those distances are equal. In fact, even the forces are also equal. Very nice. So if you know how to handle this business, it's very good. So we can draw this diagram, or whatever we call it. We can show that this is point M, which has plus 6 times 10 to the minus 9 coulombs. Then we've got a force in that direction, right? And we will have another force in this direction. And then we know that between them we have 90 degrees. And then we'll have our resultant using our tail to head method. Now, this is our resultant force. which is given to us as 2,864 times 10 to the minus 6 newtons. And we know that the distance is here, it's x, so we can just write x and x. And of course, the electrostatic forces here, we know that at this corner right here, we've got K, right, we've got K. Actually, I misrepresented this force, isn't it? Yeah, man, it's wrong like this. It's actually supposed to be the other way around. Yes, son. Okay, let me not mislead. It's important to not mislead. It is critical to not mislead anybody. Technically, the force, remember this one is pushing it. It's going to be in this direction, the electrostatic force, because they are both positively charged. And that one is going to be in that direction. So this means if we have to do our triangle mdontons, then we can put our free body, then say that would be the force due to K. And then that would be the force due to the other one, right, due to G. And of course our resultant is going to be, when we use our parallelogram method, okay, that would be our resultant there. Okay, so obviously this force is going to be the electrostatic force by K on M, and the one going up, which we can shift to here, that would be the electrostatic force by G on M. Okay, and of course we need to remember the distances. Okay, so that's key. Now we know between these two forces we've got 90 degrees, so there's our triangle. We are working with this triangle. Now it's a right angled triangle, so we can use Pythagoras to find what we want, especially knowing that these two are equal. Very easy, very nice. Again, we can do two steps. We can choose to say this force is probably P newtons to avoid a very ugly calculation, or we can actually think about doing it however we want. So if we choose to say this is equal to P units, this is fine. So we can easily say here, let the electrostatic force of, say for example, K on M equals P, because we don't want to end up with unnecessary problems. Okay, so all we know is that if that is P, the other one is also P, because they are equidistant, same magnitudes. So that's good. So this implies, or maybe we don't say anything, we know that electrostatic force, which is now the resultant here, is on the hypotenuse. So this is squared. Don't know how to write this one. You can say F resultant squared is going to be Fe, we said G on M squared plus FER, maybe let's say that Fe due to G K on M. Of course I'm dragging this thing, of course this is due to Pythagoras, okay, because we saw that we have a right angled triangle. So this implies we're given this one is 2,864 times 10 exponent minus 6, so that is nano newtons. Ibialo twin. Now this one is going to be P squared plus, these ones are equal, so this one is also going to be P all squared. So this implies that 2p squared is going to be equal to 2,864 times 10 to the exponent minus 6 all squared. Maybe let's leave it like that. And then we say therefore p is going to be the square root of 2,864 times 10 to the exponent minus 6 all squared divided by 2. Now that will give us the electrostatic force. Now let's see, this is going to be the square root of 2,864 times 10 to the exponent minus 6 all squared divided by 2. So this one gives us a 2,025 times 10 to the exponent minus 6 newtons. Nice. Now, what do we know? We know that then we know and understand that this electrostatic force is between P and M. So we can use, between K and M. So we can use that. We know that basically K, in fact, we don't even need to write K now. This is 9 times 10 to the exponent 9, isn't it? The Coulomb's constant is like this. Let me check. Sometimes my mind can play tricks with me. Yeah, Coulomb's constant is 9 times 10 to the 9. So remember, when the going goes a bit crazy, you just use whatever you have. So this is going to be into, what is the charge? This is basically 6 times 10 to the exponent minus 9 into, again, 6 times 10 to the exponent minus 9, because Q1 and Q2, that is Qm and Qk, will be that. And then we divide this by that distance. We know that this is x, but all squared. But now we are told that this is equal to 2,025 times 10 to the minus 6. And of course, this is over 1. Now we cross multiply here and get our answer. This would imply we want x. So x is going to be equal to the square root. Right? It's going to be the square root of that as a numerator, 9 times 10 to the 9 into 6 times 10 to the minus 9 all squared divided by this business right here. Is going to be 2,02 times 10 to the minus 6. Nice. Now we're going to get our x in meters. Okay, so we've got the square root of 9 times 10 to the exponent 9 into 6 times 10 to the minus 9 all squared divided by 2, 0. Hey, you don't need to. Careful of what you write. Tiredness can play tricks on you. And you end up doing a wrong calculation. 0,2025 times 10 to the exponent minus 6. Okay? What do we get? 5 over 2. So 5 over 2 is basically 0,4 meters. Sorry. This is meters. But remember, this is millimeters. So, be very careful. So, I think now that we used x here, we probably are not doing a cool job. Maybe let's just use r as per the formula. Say r. And then here we say this is r. So that we can have r, because my problem here is that this is meters. But now we need to calculate that in millimeters. Now we need to convert this thing. So you can say therefore x millimeters is equal to 0,4 into 1000, right? Because there's how many millimeters in a meter, 1,000. So that's what we do. So we multiply this one by 1/4. That becomes 400 millimeters. Answer. So again, this question was just packed with a lot of things to do, and that is why it has a lot of marks. But again, a smart plan will sort it out in just a few steps, but knowing what to do. Okay? All right, okay. Now, let's mark this thing. So how do we do the marking? This one is a bit nice, eh? Dang. Now I'm thinking. Ngathi sivele savela sesibhalile nje na iphi formula, guys. We will be in trouble here because that's not formula, yabo. Izosifaka enkingeni. Let's address that problem. Okay. Ndiyacinga ke ngoku. But somehow we need to write here, okay, Q1, Q2 over R squared is equal to the resultant force. And then we substitute. Okay? I think that's what we need to do, maybe. And say, okay, alright, okay. It's not the resultant force, but it's equal to the force. It's equal to the FE. Or maybe let's write it the other way around. I mean, it doesn't really matter if we wrote it this way. That's what we need to know. This formula needs to show up somewhere, okay? Maybe our then must migrate upwards before we run into problems, okay? Great. Now, using Pythagoras is a mathematical skill, not a big deal. What we're interested in, we can say maybe substituting and then getting that answer would be good. And then writing the Coulomb's law stuff here would be great. And essentially, and then of course substituting the right hand side as well. And we go on and find the distance. So it's how many marks here? 1, 2, 3, 4, 5. Then of course 6. So where's the extra 2 marks? Maybe setting up Pythagoras would become a good one. So 1, 2, 3, 4, 5, 6, 7. And essentially the conversion is good. Can give the 8 mark. It's not a big deal. Of course, do consult the marking guidelines to find out what is the story. But remember, what was X? It was millimeters. That's the key. So we need that X in millimeters. Although we calculate in meters and then we convert. Nice. Okay, guys, this is an easy 10 marks, of course. If you are not a shaky student in your mathematical skills, because usually questions that involve calculations in physics are going to test your mathematical gymnastics. Are they good or are they bad? And if they are bad, you break your neck. If they are good, you wow your marker, which is your audience, right? Right. Anyway, question 8 says, below is an isolated point charge, P, of magnitude plus 200 nanocoulombs. So it's a positive charge. Now draw an electric field pattern around point charge P. So that's easy. So 8.1, we know that this is a positive charge P. Now the electric field is always going away from that one. It casts it away. Yeah, we know the same thing, the same thing are doing this. So we show the electric field lines are being directed away from the center of that charge. That's it. Easy 2 marks. Meaning the direction of the field lines and the diagram itself. Easy. So let's go 8.2. It says a second point charge Q carrying same amount of charge, can you see, plus 200 nanocoulombs is placed 600 millimeters away from point charge P as shown in the diagram. So there it is. Okay. All right. Okay. Now, more importantly, we see there's also a Y point now. So we're saying Y is a point which is 200 millimeters to the right of point charge P. Okay, all is indicated. Now we need to define an electric field at a point. Now, sometimes you don't know how to do this, but we know that electric field is the electrostatic force per coulomb of charge, right? Because we know that basically the electrostatic force can be the electric field experienced by a charge at a particular point. It's EQ or QE. So if we make the electric field the subject, this is what we end up with. And normally that's all you need to say. You don't need to complicate anything. So the electric field at a point is basically the electrostatic force. Maybe you can even say the net electrostatic force experienced by a coulomb of charge at that particular point. Okay, so that is as simple as that. So you can just say it is the electrostatic force experienced by a charge. Maybe you can say a point charge or a unit charge experienced by is it per coulomb of charge, Kanin? Yeah, experienced by a charge or a point charge at that point. Yay, andazi zininzi definitions, guys. Kodwa if you're saying the right things, guys, you will not go down, okay? But make sure you master your definitions. Usually your teachers prefer that you regurgitate them, so please do so if that is the inclination, because you don't want to be found wanting over a little bit of creativity. It seems our education system doesn't like creativity. It wants static things that don't change. And yet the goal is to create innovative individuals. Sometimes you wonder, do these people ever read their mission statement though? Have they designed an education that actually provides, a nidus for this achievement? Is it a substrate for this achievement? Because if your goal is to grow bacteria so that you can study that bacteria, you need to provide a conducive medium for the bacteria to multiply, because you can't study those when they're small and they're few. You need colonies of bacteria to grow, right? So you provide them with their substrate. You can't just put a bacteria in an unfavorable environment and then you expect to see a growth. It's not going to grow. And then you end up saying to someone, this one doesn't have an infection. Because obviously a very bad microbiologist, when you send the specimens to them, who doesn't know what is important, you know what happens? That microbiologist is going to put this sample of your specimen into a wrong medium for the growth of a particular bacteria, because obviously you need to specify in your form what you are suspecting so that they can play around possibilities. If, for example, you're suspecting gram negatives and gram positives, then they can put these specimens in different media to see which one is going to grow. Because if you don't say anything, that means you're also influencing the bad outcomes, is it not? Because then the microbiologist is going to just put this thing in whatever he thinks. And then he brings you a result that says no growth after 2 days. And then you're like, okay, you're clear of infection, but your patient is dying because you're not treating an infection which is actually there. So this is what I see with our education system. It's sort of like trying to produce the best out of our students, but you can see that the very construct of it, the gist of it. Okay, I must not politic, guys. Sometimes, you know, my head spins. Especially today, I am very, very, very unwell. I don't know. How am I doing this video anyway? But it's because I made the promise. Okay, it says calculate the net electric field at point Y. Right? Due to charges P and Q. Okay, great. Now, we know that the electric field at point Y due to charge P is going to be that, in that direction. And then the net electric field at point Y due to charge Q is going to be that. Of course, the greater the distance, what does it mean? It's going to be weaker. The stronger the distance is going to be stronger. So if we draw the forces acting on point Y, this one is going to be a bit stronger. That one in that direction is going to be weaker, right? Right. We don't know how much, by how much the other one is bigger than the other, but all we know is that this is what we will have. And therefore we expect our resultant to be in that direction. Okay. So, again, being familiar with these vector diagrams or body diagrams, free body diagrams, whatever you call them, makes life a lot easier, because now you start to understand we need two opposing electric fields. So obviously we can somewhat choose to the right as positive. Okay, so usually when you're dealing with stuff like this, you must choose a direction that the one directed to the right must be positive, because you know it's going to be greater than the one to the left, because these charges are of the same magnitude. Nice. So what do we do? Well, we're going to say, well, the net electric field is going to be the electric field due to charge, say P, minus the electric field due to, maybe we can say plus, negative the electric field due to Q. Because obviously the resultant is the summation, technically speaking, but we know because these are vectors, we choose directions. So this implies that E net, as you sometimes call it, I hate that word, but whatever, is this one. So now this is going to be K QP over R squared, right? We're using the Coulomb's law, and then of course positive multiplied by negative is going to just be KQ Q KQQ yewena awayiva into entry zange ndayiva. All right, we just continue. E net, this is 9 times 10 to the 9 into, this is 200 nanocoulombs times 10 to the minus 9. Okay, good. All divided by, now that distance here is 200, so we divide by 1000, so that's 0.2 all squared, minus, this is 9 times 10 to the 9 into 200 times 10 to the minus 9, all divided by, this one is going to be 600 minus this thing, right? So that would be, you can show this calculation that this is 600 minus 200, all divided by is squared. Okay, and then we're squaring it, because we're just trying to do less work or less steps. In fact, here we can just put it down. We can put it down and say, therefore our E net is going to be, now let's do it on the calculator. So we've got 9 times 10 to the exponent 9 times 200 times exponent minus 9 divided by 0,2 squared. Then we subtract this whole situation as well. But make sure your substitutions, folks, are good. So we know that 600 minus 200 is going to be 400. So that would be 0,4, right? All squared. Let's see. You see we're getting a positive answer, which confirms we're doing well. So this is 33750. Now what is the unit of measurement? Is newtons per coulomb. Okay. Yes. From the definition, it's the force experienced by a charge. So that's newtons per coulomb. Nice. So obviously, guys, sometimes we get a mark for these substitutions, but more importantly, this one was a calculation on its own, so that would be a mark also. The question said the net electric field. Now remember, that is a vector. So what must we say if this is a vector? To the right of point Y. Please be specific. A vector must have the respect it deserves, so be very careful here. So we have 1, 2, 3, 4. Perhaps we can get an extra mark for this one. But remember, we also need to mark the formula. So we can say, well, 1 mark there. So that would be 1, 2, 3, 4. 1, 2, 3, 4, 5. Yeah, 5 marks. So this means the last mark must carry the right unit and the direction. If those two things are not present, you lose the last mark. Okay, it's not a joke, guys, it's a reality. So that would be 10 marks of this question. Nice and easy. As you can see, guys, these questions are not too difficult. So they just demand you to be careful. Alright, so I hope we are cruising nicely and you can follow on properly. So I wanted to use that as charge P. Okay, now let's get to the complexity of the electricities, because hey, yeah, it can get a lot hotter. It can get a lot of hot. Obviously, we will know how to deal with it. Now, the battery in the circuit diagram below has an internal resistance R, so that means it's a potential question already. When the switch S is closed, the reading on the voltmeter is, now remember closed, the reading on the voltmeter V2 is 8 volts. Now let's see, what is V2? V2 is across the parallel resistance. Can you see? Because even though this looks like there's a separate one, since there's no two resistors on one line, it means these two will experience the same voltage. So this is the examiner trying to confuse you. V2 is nothing but V parallel, because the same voltage there should be the same as the one on the 12 ohm resistor. But of course, we have a 10 ohm resistance which has its own separate voltage. Nice. Now we're told that the resistor R dissipates this amount of work. Okay, so that's good. So we know that the work here is 13,5. In fact, it's not work, but this is watts. So that is power. This is actually power. So this is most likely a light bulb, isn't it? This is the brightness it gives us. Okay, now that's it. Alright, so we know that the long bar is the positive, the 1 bar is the negative, and we can see this is just a single cell. So this could be some remote control or something. Anyway, the current, conventional current, goes in this direction, passes through the ammeter. When it gets here, it splits into two different dondons, and then they go through each resistor and come back to join each other there. Okay, so they join there and form the main current. So meaning the 10 ohm resistor experiences the total current. Nice, not a big deal. So we know that voltmeters are high resistance. Thing is, there's no current that passes through them, so it doesn't bypass the battery. Okay, so that's it. We have our understanding of how things are going, and we know that we've got a parallel connection here. So of course V1 is the total external voltage. So this one is the total external voltage, meaning the V parallel plus the V of the 10 ohm. So we can call it V external. Nice. Okay, so we can start. What does this story say? Now it says state Ohm's law in words. This is a grade 10 stuff. So Ohm's law technically, guys, speaks about the current and the voltage over the resistance. Now, when we talk about this one, we are saying this guy is constant, but we don't use it directly. We use a surrogate, which is the temperature. Because if the temperature rises, the resistance rises, isn't it? Or a higher resistance results in a higher temperature. So that is the story. So if we keep this constant, then we know that current will be directly proportional to the potential difference. So that is the Ohm's law, essentially. So we can just say the current in a current containing conductor. But don't say a lot of things. Just say the current between 2 points. Let's just put it that way. The current between 2 points in a conductor is directly proportional to the potential difference. Potential difference between those 2 points, provided the temperature remains constant. Okay, good. So this is a bit wordy, but it's not bad. Okay, now if you think about it, the temperature is a surrogate measure of our resistance, because we know temperature will affect the resistance. Nice. So we say those things. So basically we talk about the direct proportionality of the current and the potential difference between 2 points in the circuit or in the conductor, provided the temperature is constant. So that is worth 2 marks. Nice and easy. 9.2 says, now calculate the resistance of resistor R. Can you see? This is just 3 marks. Now if it is 3 marks, what is it indicating? It's showing us that we should know what is cooking here. We are not supposed to sweat. But now my problem is, how on earth do we not sweat? How do we not sweat? Because if it is 3 marks, this is suggesting that we are not sweating. Of course, we have the reading of V2, but we don't have the current on that side. So that could be a problem. Ne? That could be a problem. Oh my lord, I forgot. This power is not for that. Bad execution. This power is for this resistor R. So resistor R is probably a light bulb. Now I'm happy, because we know that power is going to be V squared over R, isn't it? That is the best formula. Now we were told this is 13,5 equals the voltage we were told is 18. We're squaring it over R. So therefore our R, when we cross multiply here and do the things that we need to do, of course this is over 1, R is going to be literally 18 squared divided by 13,5. Nice. So let's see. We've got 18 squared divided by 13. Oops, 13,5, not 135. So that is 24 ohms. Okay, so formula substitutions, answer must carry the right symbol for the measure. Okay, these are 3 marks. So 9.3. We need to calculate the reading on the ammeter. Now that's a bit of a question. It's not a nice question. Okay, it's a nice question, but it's not an easy one per se. So how are we going to do this one? Of course, there's 5 marks there. It's already telling us that we need to perform some serious gymnastics. Well, we've got 2 options. We can calculate the current here, say this is I1. We calculate the current here and say this is I2, and then say this one is I tot. Okay, good. So we can use that same voltage. We will get the current I1, say same voltage, and this resistance, we calculate that. But what if this resistance is incorrect? Unfortunately, we cannot escape it, can we? We can't. We can't escape it. So we just have to deal with it, okay? Because the calculation is centered here. Nice. So for me, I would say, well, to calculate the total current, I would simply say V parallel is going to be basically I total multiplied by R parallel. I'm just going to use this so that I can just do this in one step. Now this thing is what? We're told it's 8. This is equal to the current, which is what we want, into, now R parallel, there's 2 resistors, it's usually product over sum. So this is going to be 24 times 12 divided by the 2, which is going to be 24 plus 12. See, makes life a lot easier. Now, what do we see? We can say, therefore, the total current is going to be literally 8 divided by this situation here. Okay, so what is this? All right, okay, all right. So this is going to be 8 divided by 24 times 12 divided by 12 plus 24. Uzozo moya. Sithola u1 qa. Untshwe. Yewena. It's just 1 ohm. 1 ampere. Hayi ingathi strange nale answer. Impendulo yami ingathi ifuna ungiqhela. Kutheni snacks kanje? I don't trust it, eh? I really do not trust it. Let's see. Lento lenis of flip 8 times 24 plus 12. I don't know. Turning at if important divided by that product of 24 times 12. I still get 1. You win. I have fits. Turning at over. If we want to change 1 vel, let's try the other technique. Sometimes when the answer is a bit fishy, check the other technique. What does it yield? Now, if we use the other technique, what do we see? We can just say the I2, if we want, it's going to be V parallel, which is 8, divided by the resistance of R. So we said this is I2, which would be 24, right? So this is basically a third, isn't it? Yeah. So 8 divided by 24 is a third. So this is 0,33333. So this is 0,33. You know? Yeah, masiyeke khona lapha. Actually, masinga round it off at the moment. We leave it like it is. So this is going to be 0. It's a third amperes. Ne? Not a problem. Now I1 is going to be 8 divided by 12. Right? What is that? That would be 2/3. Now 2/3 is 0,67. So maybe let's do this one to 2 decimal places. This becomes 0,33. Then this becomes 0,67. So what would be the total? So we can say here 0,67 plus 0,33. Hey, kusaphuma 1. Hayi ke bafethu, if siyenza ngale ndlela iphinde iphume ngale ndlela, then it means we are correct. So this means we are correct. Okay, maybe let's leave this one as a way of checking, But it looked too simple and too easy. Strange stuff. Anyhow, we move on. So that would be the ammeter here, basically. All right. So 9.4 says, explain in words what is meant by the term internal resistance of a battery. What is the internal resistance of the battery? See now, a lot of definitions are coming in. So this is basically the energy dissipated when the current passes through the battery, basically. I don't know how to put it, guys. It's one length. It's again the liver for Nelkamal boson. What is meant by internal resistance of a battery? It means the battery. And in fact, I like the part that says explain, meaning it doesn't really want a definition per se. We can say the internal resistance of the battery signifies the fact that when the battery is in operation, energy will be dissipated within the battery due to resistance of flow of charge. I don't know how to put it, guys, but we can say the internal resistance of a battery simply means that it means that there is energy dissipated in the battery, in the battery due to the resistance to the current passing through. Yeah? Obviously, guys, we know that. Where's the higher potential again? Because remember, we always say we move from high to low potential, right? So now remember, we have a high potential here. And this goes all the way to the low potential. But now we're going to go against a potential gradient here. And that is actually the resistance per se. It's not a true resistance, but it's because we are moving charge against a high gradient. Because normally we move from high to low. But this time we're moving from low to high. And that is the reason for this situation. So I don't know how to explain this in words, but I can put it this way, that it means that there is energy dissipated in the battery or within the battery due to the resistance by the battery. Maybe we can say due to the resistance by the battery to the current passing through when in operation. Yabona yongo. Sifaka konke, sifaka namahlahla. Ngixesha funeka uqokele, ithi sathi ithi yavika uqokele, kubethe enhloko uzazichani uwele phansi, yabona? If awuqokele ubetha kubekanye ulindi izawuvuka ngamanye amandla anzima ikunyathele emqaleni. Ayifumani? So do it. So guys, I think as very crazy and cryptic that may sound, of course, this means revise every definition. But sometimes certain things they just want you to give, because remember this one said explain, it didn't say define what an internal resistance is. It just said explain what is meant, you know. So it just simply means that there is some energy that gets dissipated within the battery when that battery is in operation due to its resistance to the current passing through. Right? Okay, now let's go to 9.5. Hey guys, the tiredness I cannot imagine. Calculate the potential difference across the 10 ohm resistor. That's easy. So this implies that V, the current we found out it's 1 amperes, then this is 10. So therefore, V weight is about 10 volts. Okay. All right. Okay. That is nice. That is beautiful. That is great. You see. That is the thing. Okay. All right. Okay. Whew. Nikarele nkopfu. Hey. Now when switch S was opened, the reading on voltmeter V1 is, now remember when the switch was opened, the reading on voltmeter V1 was this one. What does that mean? This is the EMF, because when switch S is opened, there would be no current flowing, so the terminals would read the EMF. Now we need to calculate the internal resistance of the battery. Very easy one, okay? Formula, substitution, answer together with the correct unit. Hey guys, I'm dizzy, man. I'm dizzy again. I thought I was going to be stronger. Now I'm feeling dizzy again, okay? How do we do this? Easy guys. We know that the EMF is going to be equal to the total current into the external resistance plus the internal resistance. Now this implies this is now 45.9 is equal to, now the total current, we found out that the total current is what? Is 1. And then the external resistance here is what? This is 10 plus that product over sum, isn't it? So what was that product over sum? You see, now we should have gotten that one. We should have gotten it, but anyway, we can still do it and say this is 24 times 10. It's not a big deal. It's not out of reach. We've got 24 times 12, over 24 plus 12. Right, plus R. Okay, I'm just lazy to separate things now. Okay, taking it easy. So we've got 45,9 is equal to, so we can sort that out. So this is 10 plus into that product 24 times 12 divided by 24 plus 12. Right. This gives us 18. So this is 18 plus R, because that is 1. Therefore, the internal resistance is going to be the difference. It's going to be 45,9 minus 18. Yeah, it's quite big, eh? It's quite big. It's a 27, a whopping 27. This question is wrong. Guys, saucy. We have never seen an internal resistance this big. I can mean, guys. Can't doing it right, la. And so also 20 don't ohms. Guys, no. I have never seen this. Is it possible? Nah. I'll just get something is not adding up, guys. What happened here? Something is not right, huh? Did we perform some incorrect gymnastics here? I mean, here we substituted, okay, the voltage was 18, that was V parallel. Okay, calculation looks okay. Here the current, God, I put 8. No wonder we were in trouble there. Yes, okay. But again, guys, you can see though the quality of the answers. I mean, we have never, although it's possible, but I mean, it doesn't make sense, does it? So then that battery is ridiculous. I mean, can't have so much resistance. It will waste the power before we even get it. So that is not good. That's not a good battery. So no. I knew something was not right, man. So I put an 8 in here. So this is supposed to be 18. Lord have mercy on me. So this is 18 divided by that product, which is 24 times 12, divided by the sum, which is 24 plus 12. Okay. So you can see marks can easily be lost here. This is 2,25. Game with up. So this current is 2,25, folks. Easy marks, just trying to get out of the window. But of course, you guys have what you call the positive marking. At some point, if you did that mistake and you didn't notice, you would lose the marks for that one, but you would actually be given full marks for the subsequent calculations because you used what was there. Although it looks crazy, but I don't like that positive marking, because I mean, you're getting all the marks for the wrong calculations. No. Okay, that one looks a bit better. So this means we would multiply this one by now 2,25. Okay. Nine to villain palega bench spacing. Yan papela. Yan papela again. Okay. So we need to change that. Say times 10. That gives us 22,5. Okay, everything changes. Volts. Remember, we need to have volts. I don't even remember what I put in there. Anyway, now all changes. But it's not a lot. Okay. That's why in this bulal. Don't need to kill myself, So this is 2,25 into this is 10 plus that. Okay. Now everything is going to change here. So sometimes I'm happy when you get questions like this that build up from the previous, because if they are separate, you wouldn't notice you're losing those marks. Now this scaffolded type of questions actually provide a rescue therapy. You save yourself here. So, well, we can do this one nicely and say this is 2,25 into 18 pi plus r. Yeah, I just born a 10 plus that situation there. Why you guys entertaining, man? I'm not really focused fully. I'm feeling a lot tired. So hey. Oh, because I'm the substitutions they're betraying me now. Yeah, 18. Okay. Now we can divide by 2,25 here, and then we will have 45,9 divided by 2,25 is equal to 18 plus r. Therefore, r weight is going to be 45,9 divided by 2,25, and then we transpose 18. And let's see what is that. Okay, so we've got 45,9 divided by 2,25. That gives us 20,4, and then we subtract 18. We get 2,4. Okay, that is not so bad. 2,4 ohms. Okay, that feels a bit better. I mean, if a battery can dissipate has a resistance of 27, imagine that battery is exhausting most of the power within itself, and it's not providing it for the circuit it's connected to. So that would be bad, and we can't have a battery like that. That battery is old if it is like that, and you need to throw it away. All right. This is like an old battery. The resistance keeps rising, and therefore it just goes flat quickly. Anyhow, let's keep moving, guys. We're almost there, even though we are not there yet. Oh, we were scoring some marks. That is the mark. And this total calculation of the external voltage, that's a mark. In the general substitutions, that's a mark in the final answer. So this is 1, 2, 3, 4. Where's the fifth one coming from? Or to know that this is the EMF, because it was not clearly stated. That would be the fifth mark. Okay. Nice. That could have gone very bad, eh? So tiredness can do it. Does the internal resistance of the circuit increase, decrease, or remain the same when the resistor R is removed? Well, this is easy. The internal resistance is specific to a particular battery, so it remains the same. Okay, because that thing together with the EMF do not change. You need to know that. So, I mean, I like these questions though. I mean, this paper was somewhat interesting, if not interesting. Ne? I'm sure you agree. It's a bit challenging. It's a low-key challenger. But again, mistakes are just another issue there. Okay. So let's get to the electrodynamics, guys, which is where usually some easy marks can be scored quick, you know. Yeah. All right, folks. Hey, Yane. I'm taking quick breaks every now and then because I am suffering. I am suffering, guys. Okay, let's go on. What is the story? So study the sketch below. What do you see, guys? Obvious. You're seeing a split ring commutator. The split ring commutator is already telling us we are having a DC something. Direct current something. Ne? But now, is it a generator or is it a motor? If we see a Bretty, it means we are providing an external source of energy. Now we are converting electrical energy into some mechanical energy. So this means we are using this like a hair dryer, right? Ufaka lento kwi plug bese press a button say ya spin lento ivutela umoya. This is more like it. So now this is a motor. So this is a DC motor. It says now write down the function of the component labeled Q. Upi uQ. Yabon? This is the split ring commutator. Now the function of the split ring commutator is to ensure that the current flows in one direction. Okay, so that is the story. It ensures that the current flows in one direction. Okay, as opposed to a alternating current where the current changes direction. So easy one, Mark. That was 10.1. Okay, 10.3. So we're seeing a graph. And what is this graph? It's a sine graph, it seems. All right, okay, all right. So this is an alternating current, so to speak. Now something says two changes are made to the structure of the device above. So that means we're modifying it. Now, to obtain the following output potential difference. Now, once the output potential difference is alternating, what does that mean? We changed this into an alternating current device. Now, for a DC motor, the potential difference we expected was stuff like this. And so on, okay? Now, you see it's not like that. So, it means we changed it to an alternating current device. Now, the question is, hear this thing. It says output. See that one? Output potential difference. So if we are creating voltage, what does this become? A generator. So we converted a motor, a DC motor, to an AC generator. Because we have this output potential difference. And it's an output, not input. Ne? Think about it. So obviously, if we're producing this, that means we're also producing current, essentially, because that's the idea behind this. Okay, it says write two changes that were made above. Okay, now the first change that we may have made, maybe let's use A. The first change, we will replace the split ring commutator with slip rings. So we replace the split ring commutator with slip rings. Okay, slip versus split, that's one mark. Ke mmaraka ya ho qala ya mathomo ntwani, ke mathomo, ke mmaraka ya mathomo. Ke efeng e latelang jwale? Ke efeng e latelang? Remember, we created a generator instead of a what? So what else can we do? Well, guys. Instead, we can put a light bulb here. We can connect a light bulb or something. You see, we can replace the battery with a light bulb. Maybe replace the battery. Replace the battery with a light bulb. Or any form of resistor that can tell us there's a current passing through here. Because the pivot is already saying that we are inputting mechanical energy there. Or we can put a lever there that we can use to do the things. So yeah, we can talk about that because we don't see a lever here so that we can move this one mechanically to generate this. So we can also say you can add a lever to rotate the coil or something. Nice. Okay, so 10.3. When telling a type in general question. Now it says a 60 watt light bulb is connected to the new device, okay? And a peak current. See this one? What is this? A peak current of 0.54 amperes flows through the light bulb. Now, calculate the potential difference of the DC supply that will produce the same brightness as the light bulb. Can you see? We want the RMS voltage, basically. That's what this means. They're just confusing us with this. The idea is that we know that the RMS voltage is the equivalent of the DC that will supply the same energy, isn't it? Yeah, man. That is the thing. That is the thing that we must do. So when we talk about peak, we want RMS current so that we can do the RMS voltage. You see? But now with the work here, we can use the work to find the resistance there that can help us to do this thing. So this is a 60 watt. 60 watt. We know that power is not too bad, ne? But there's too many conversions here. The marks are basically from the conversions. And this level is a formula, ne? But remember, we've got the current. We want the voltage. So let's see. We know that the power formula, average power, is going to be V squared over R. Right? But we don't have this one. We can say this is VI. Because we don't need what is not here. So this could be VI. But now this must be IRMS. Ne? VRMS. Because it can't be anything. This is average. Power average. Maske sijonge. Where are you? Are you trying to hide? Out is born. That is the one. That is the one. That is the one. So this is the stuff that we need to handle. And as we can see here, max means peak. So that would be peak. So now to get the RMS is going to be the peak over the square root of 2. That's the one thing we need to do here. Otherwise the power doesn't change. then the VRMS is what we want. So this is what we are going to get. Ne. Excellent, brilliant. Injalo nje. Ayingxengwanga. Yayiva yango. Yeah, ayingxengwanga. So this implies we've got the power there, which is 6CT. This is equal to the voltage. What is this voltage? Is what we want. RMS, root mean square. But this one, to get IRMS, we take the current, the peak current, which is max. We then divide it by the square root of 2. And then we do the things. Therefore, our VRMS is going to be essentially, technically, and by the way, zonke bonke is going to be 60 divided by this business here, 0.54 over the square root of 2. Then we will get the voltage in RMS. Remember, RMS voltage is the equivalent of the DC in dons. So we just do it. So this is 60 divided by fraction button 0.54 divided by the square root of 2. We close the brackets and we get our marks. It gives us a 157, to 2 decimal places 13 volts. Are we happy there? I think so. So this one is a mark, by the way. This calculation or conversion is a mark, and the substitutions is a mark, and the final answer. We're turning 5 marks. Are we supposed to convert something? Nah. I'm trying to think now, guys. Do we really go back to the peak? Are we supposed to do another conversion? Hayi bafethu, angazi. Iphi kanti lento? Where are these marks now? Anyway, anyhow, I don't know, guys. Maybe 2 marks for the answer. You know what? Ngikhathele manje. Senasikhathi mina. Akusana nako. Ngitlola 2 marks because technically this conversion would yield some answer, but we did not choose to write it. So we'll get full marks if this answer is correct, you see. So this is going to be 5 marks. I mean, this is not a heavy question. It's just a silly question, that's all. So, maske siyibone ke guys. This is now 8 marks. And you see, electrodynamics can be a stress reliever if you feel like you are being boxed by the big boys. But at some point, you're going to have to deal with the big boys after another and after another. Okay, guys, masiqumbele ke ngokulento. Let's song it. Let's song it back to its owner. Now we are just going to fold it and finish this thing so that you guys can practice well. All right, so it says the photoelectric effect has many practical applications. Yes, we know. Mainly in medicine, it's radiotherapy. This is X-ray treatment. We use cobalt linear accelerator. You see, that's what we call LINAC. It's a linear accelerator. So this is when we're treating deep-seated lesions like in the brain or in the brainstem where you cannot operate. You can actually focus radiation right in there. And of course, using the photoelectric effect. So high energy photons will hit those cells of the tumor there and destroy them and cause irreparable DNA damage. And then subsequently, we know that once a cell loses its DNA integrity, it actually is signaled in the pathway we call the apoptotic pathway, where the actual cell just dies or cancels itself out. It's like cell suicide. We call it a cell suicide. It kills itself, basically. So cells are programmed to kill themselves when something goes wrong. It's like a mission by some soldiers, you know. If you get caught, you kill yourself because you can't tell, you can't give the intelligence as to how our operations are going. Because when they torture you, you're going to talk, isn't it? And unfortunately, nowadays we don't get that. Cancers are the ones that resist that apoptotic pathway. So there's an attempt by the cells to repair the DNA, but now because of incorrect repair, now certain genes that actually upregulate, then they create cancers or cells that divide uncontrollably. And now you end up with a problem of a cancer, right? So radiotherapy can actually cause cancers elsewhere while it kills the cancer being targeted. Because remember, if you're doing just general whole brain radiation, that means you're also irradiating other normal structures. That means you can transform that DNA because it won't get the same measure as in the center of the radiation. So this thing of focused radiation, when we're using things like gamma knife, we call it the gamma knife. The gamma knife. Now this is a form of what we call stereotactic radiation. Yawena ndifundisa into eningazazi ngonizozazi ke seniyazazi futhi ngo. Now stereotaxy, it means you target a specific region, even though you have your brain, cerebellum, and then you've got your brain stem, and then all of the mass of the brain there, and then you've got your cerebellum there, and then you've got your brain stem. So if you've got a lesion right there, we can put collimators around that center so that they all converge at that thing. So all the photons that we irradiate from this, someone wears some head helmet, so it accelerates those cobalt atoms or electrons in there, and then they deliver energy specifically to that region. So that means you can actually deliver a high dose energy to that brain tumor there and destroy those cells so badly that they cannot escape apoptosis, and therefore they commit cell suicide. And now as those things die, the normal cells will clean up that thing by scavenging on the debris, and guess what, 2-3 months down the line you find that the tumor is gone and someone improved the neurological fallout. So these things are very, 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 very important. Of course, here you make them wear some helmet that is connected to machines that actually, what happened? Yeah, bana we buyela ngapha we yabona ngiqhela kabi. Kwenzeke ntoni pha? Hey, yangiqhela. Okay. Does as long as yangiqhela, but I'm learning anyway how to use these things. So you will see that there's, collimators all around on the helmet that you make someone wear, and then you put them on the machine, and then you switch it on, and then this activates those energized photons, and then they start doing the thing. So this is the one that is practical to medicine. Okay, yeah, that is the one. Okay, all right, okay. Usually X-rays and CTs, not necessarily this photoelectric effect per se, but it uses the shadowing kind of things, characteristics, because as you illuminate something, let's say you've got a shadow like this, and then you put light onto this. On this side, you will cast a shadow of that which you put a light on. So we start to see this on the screen, and then we read this as the X-ray. Usually this is what we see. So it's the shadows that sometimes we get when we shine on the other part and what. So there's a whole lot of things, but the physics behind these things are very important. Actually, I saw someone doing a video. I don't remember that channel now. Quantity. Is it Smart Tutor? Something like that. But he was doing mathematical modeling. I thought I was talking nonsense when I spoke of that word. Sometimes my ignorance is ridiculous in that it's usually in the right direction. Anyway, he spoke about mathematical modeling when talking about a bubble. Now, that was a bubble talking about the pressure inside the bubble, talking about the surface tension on the bubble, and then talking about the pressure outside the bubble. Now, obviously, we know that if the surface tension decreases, the bubble increases in size, provided the pressure on the inside is bigger than the pressure on the outside. So if we release the tension, meaning the tension is what keeps it together or small as possible. So if we decrease the surface tension while the pressure inside increases, we know that this is what happens. But of course, if we decrease the pressure on the inside and we increase on the surface tension, the pressure outside will also increase, meaning the bubble gets smaller and smaller. Now he was asking, he did a formula that actually proved this kind of a relationship. Now he was asking a question that, okay, but when would you be studying bubbles and stuff like that? And then I was like smiling and like, oh man, if only you knew. These medical doctors need to work alongside these engineers, you see, so that we can create machines that work. Because remember, when you're ventilating someone, you've got the lungs. Then you've got your enthesio's there. Now, if you've got the lungs there, you see on the lungs, you've got alveoli. These are like little balloons, okay, from the main channel of the airway. And then you've got them little balloons all around from the main airway. And guess what? There is surface tension. It is kept by what we call the surfactant. Now, the surfactant decreases the surface tension so that the alveoli, the balloons, can expand easily. This is what makes your breathing very easy. But when you're sick with flu or pneumonia, this gets destroyed, and therefore the surface tension increases. That's why you see when people breathe, you can see the muscles of the neck, even the intercostal muscles, indrawing in small children, because now the labor of breathing is harder, because now to expand, the pressure on the inside is going to require a lot of work because of an increased surface tension. This is where the ventilator comes in. It injects some PEEP, we call it positive expiratory pressure. That means even if you evacuate this airway, it doesn't become this small. It remains maybe that size from this, because you are leaving some positive pressure within the airway to avoid a collapse, so that when you ventilate, it's easy. So you don't end up blowing these airways, because if they can reduce to this, if you're going to force pressure in here, then you're more likely to give more than is necessary, and then they blow up, and someone ends up with a lung injury. Call it an acute lung injury, or early. And that person will go into respiratory distress despite the ventilator and die. So essentially, guys, these things are very, very, very useful if you think about how they work together and stuff. I'm sorry, I took a diversion, because you see, most this guy likes to educate. I don't know why. I should not do this thing, actually. It should not happen. You need to find out when you get there. But of course, I'm just trying to say, please, engineers, don't isolate yourselves from the Dopplers, because trust me, one day we'll be trying to get, a machine that treats something that is not treatable currently. And that can help us if you guys work with us, you see. Because we can tell you what is our intention with what we want, and then you think of ways of developing that using your mathematical modeling, because that's the essence of maths, actually. Then we devise some machines using all the laws of physics and knowing electrons and atoms. And at the end of the day, we get something that is easy. Maybe you can have a handheld CT scan, that when somebody is sick, someone can just place this thing maybe on the nose, and then it can show us the whole cross-section of the brain, instead of needing a big machine that sits in the room there. That means even the surgeons, when they operate, they can actually trace the progress of the operation. Are they winning? Are they losing? Are they even getting out the lesion completely or not? So these things will use the photoelectric effect, because we can use this to generate pictures as well, or 3D reconstructions of the structure that we're dealing with. Yeah, because this is what happens. First, this thing will design a 3D structure of the lesion. It will even tell us in 3D. If you turn it, you'll see that it has bubbles and stuff like that. You find that the tumor has all of those things, especially things like cavernoma. They look like a bunch of grapes in the brainstem there. It can tell us exactly how it looks. Then you can actually design a model now from this to try and irradiate every little bump you see in this thing. Instead of hitting normal tissue, you can actually create a model like this, and therefore you know that you're focusing radiation right on the lesion. So you guys can become very useful as engineers, so you don't work in isolation. And believe me, we could make a lot of money if we work together, but of course, you know how black people are. Their egos are too big for their own good, because the one who's a doctor is going to pretend is better than the engineer, and the engineer is going to feel like, you know what, I can compete with that bastard. And at the end of the day, it's just a bastard-like competition, and it doesn't yield anything, because how many engineers do we have in the country? especially black engineers. Let's not talk about color per se, but I'm just trying to highlight something here. You see, there's plenty of these guys. How many doctors do we have? We have lots of doctors compared to white doctors. But do you see any creation being made? Nope. It's very bad. At least Prof. What's his name? Prof. Chipolaro, the ENT surgeon who created those implants. Those are 3D printed things. That means it used some mathematical models and engineering. So congrats to those who work with him or worked with him, because now they started to cure deafness, something that has not been done elsewhere. Okay. All right. So this is what becomes the results of working together, collaborating, instead of becoming ridiculous and compete for success and living in large and big houses. What does it matter when your country is in shambles? Because that means you will be unsafe even in that big house of yours. Be careful, guys. Don't be too individualistic and too consequentialistic in approach. Be more of a Kantian type of a philosopher, where you have a sense of duty to make a difference. So if you are duty bound, even when you don't like it, you will do it. Okay. So that means you need to work with others, use their skills, combine with yours, have a common achievement instead of an individual achievement. So that is what is defeating us, the darkies in this land. Instead of working together, we want to fight against each other. If something works out when we do it together, guess what? Someone is going to claim it is because of their hard work. The others are not doing it. Yes, you can win this round. Sometimes we can stay afloat in our company or in our cause because of your contributions. But it doesn't mean every time there's a problem, you'll be the only one. Sometimes tomorrow you won't even have a clue of what to do. And then someone within the team will rise to the occasion, because God gives us different opportunities at different time intervals for a different purpose. Sometimes you may be the regular one, of course, most of the time it's you, but it doesn't mean you are better than the rest. Because what would you be with your ideas in the absence of the others? Because remember, the execution is not only you alone, it's everybody involved, and fully so. Anyway, guys, I'm just trying to suggest that, look, engineers need to work alongside the health professionals. Health professionals need to be aware of what they need to do, meaning you need to know things properly. Don't just read books. This is pneumonia. This is how you diagnose it. This is how you treat it. But you just blindly read on the book. What happens when pneumonia presents like it's something else? Or what happens when it is masked by liver failure or maybe seizures? Would you still be able to recognize that this patient has a pneumonia? I don't know. That's why you need to know things, so that even when you see this complex or syndrome of things, you can tell who is playing a part in there and be able to deal with it properly. Otherwise, remember, time is brain. If you miss time and you don't correct what is affecting the brain wrongly, that person is going to die. And you will find out later on a post-mortem what you should have done. And that's sad, because a family has lost somebody because of your negligence. Why? Because you thought you know. Because you think you can just cram on the books and come back here, pretend to be what we need. We don't want that. Bafethu. Ngiyanibulala futhi ngiyanibulala kodwa ngiyanifundisa yabona nifuna nizazi izinto guys, ningabi weak, because sebebaninzi abantu aba weak la. They are weakening our strong profession, because almost everybody is in here. And the sad part is that not everybody is as useful as we need them to be. So be that useful, folks. So this thing sparked a serious discussion. Anyway, let's leave the stories, guys. I'm sure you get the story. Now, a photocell such as the one below used in burglar alarm systems. Okay, photocell such as the one below used in burglar alarm systems is one such an application. Can you see? It applies even outside medicine. There's plenty of things. Of course, it will take your awareness to know that these things are actually working in that way. Now we see an ultraviolet beam here. It hits the anode. oops. And then it is as it hits the anode, what happens here? We can see, hey, turning at is fun, turning at is fun, go. As if as the electrons is here with cathode, is with cathode, is here with anode, here when. Sometimes the photocell and popanis, anyway. But we can see electrons are accelerating towards the anode, okay, whatever. But then it means, oh yeah, this means this light, okay, if I can go. I wouldn't confuse it. By bege up is on biases are corner. Now we biases are the same way. Now you see that thing is placed where you could get confused. Actually, these light beams or these ultraviolet beams are actually hitting the cathode plate. Then this strips electrons which accelerate towards the anode. Now that makes sense. And of course, we'll see a current, right? Right. Now, obviously, conventional current is doing its own things like that. You see the direction of electrons is actually from the negative to the positive, but conventional current is the other way around. This is why sometimes you wonder certain things, but there's a way of explaining this. I'm not going to get into it. It's boring. But anyway, the idea besides or behind this whole thing is saying that if this is what happens, for example, if you think about it, if electrons are going, say, how do I chaza this thing? Okay, must I complicate? So because I will not finish. Now I need to finish. Now it says now the largest wavelength of monochromatic. Now monochromatic, it means one color. Mono means one. Chromia means color. So this is one color light. It's not a multicolored light. You see, it's a monochromatic. It means one colored light, like white light, that will cause the ejection of photoelectrons in the above photocell is 229 nanometers. Now when a person interrupts the beam, the sudden drop in the current activates the switch. Can you see? Very interesting stuff. So it says when a person interrupts the beam, this is a thief trying to open here. Now he interrupts the beam of light getting there. Now what happens is the current will drop. Why would it drop? Because less photons will hit the cathode. If there's less photons, then there's less electrons released, and less electrons means the current drops. You see? Makes sense. Okay, all right, okay. And then it sets off the alarm, and then and then the bastard gets caught. Okay, calculate the frequency of the monochromatic light of this wavelength. Okay, that's easy. That's easy, because if we've got the wavelength, what is the story? We know that the frequency is the reciprocal of that one. So, so we know that the velocity, but now we say the speed of light is a c. It's going to be frequency multiplied by lambda. Yes, this is the one that we need to use, because I almost took the period and I was going to get into trouble here. Okay, so this implies now this is what can go 2 times 10, or is it 8 times? I think it's 2 times 10 to the 8. I must say wrong before says Bulal. What is the speed of light in a vacuum? EP, speed of light in a vacuum is 3, not 2. See, I still have some memory there. Imagine you guys have been doing this all the year through, so it should be fresh in your mind. You should not rely on this too much. 3.0 times 10 to the 8 is equal to the frequency is what we want, multiplied by the wavelength. But now the wavelength has to be in meters. Now this is nanometers. So this is going to be 229 times 10. Nano means to the exponent minus 9. Yes. Therefore, our frequency is going to be 3 times 10 to the exponent 8 divided by 22.9 times 10 to the exponent minus 9. So siyibethile 3 times 10 exponent 8 divided by 229 times 10 to the exponent minus 9. Hey, names in a frequency. It's a very high frequency, this one. So this is 1,31 to 2 decimal places times 10 to the exponent 15 hertz. It's very high. It's very high. It's doing the things. So formula, substitution, mainly this conversion technical. And the answer with the correct unit. Remember that. These marks are easy, but they can be lost quite easily as well. 11.2 says, give the scientific term for the frequency that was calculated in question . What is the scientific term, guys? Threshold frequency. Because this is the minimum. You see, that would be threshold. So we call it threshold. Is it threshold or is it threshold? Yeah, I think it's threshold. Is that so? Aye, think at in the level come and you balance and go threshold wasn't go threshold. Hey, that pagana negam, yabona my vocabulary is escaping me. Yabona. This is I think it's threshold frequency. I get buffet nanis was born. Little iponela lilo na go letsa biana bianong hobane nna ke popane jwale. Ke nahana re mhlonyane ne ya ka ya mpola jwale. Empa e beterenyana mhlomong ho bua thata ho a thusa ba bona. Waneng ho nna fatshe kampa ho robala betheng ke ntse ke mametse ntweng. Tlampola ka nnete baneng kenyetsa le stress hona tjena. Define the work function in words. See now, this is a common word. The work function in words is what? This is the minimum energy required to strip electrons from a metal surface. So work function is the minimum energy. Is it energy required to emit electrons from a metal surface? Is it surface or is it surface or is it surface? Surface, man. Surface this thing. Okay. That is the stories, man. It's not too big. It's just 2 marks. Nice definitions. Can you see this topic is just a walk in a park? Now we need to calculate the frequency of the monochromatic light that must be used to emit photoelectrons of this particular velocity from the cathode of the above photocell. Yeah. It's a funny frequency foot. Yes. Asibalanga naganti. Oh, that was the largest wavelength. Now, remember the largest wavelength is hey, Mark. Konja, what's the relationship between the frequency and the wavelength? Yeah, man. The largest wavelength, that would be the minimum frequency. Ne? Because if the wavelength is the largest, that becomes minimum frequency. Ne? So I'm not so sure. Is that correct to say threshold, the scientific term? The largest wavelength of a monochromatic light that will cause the ejection. Yeah, man. Yeah. Because the smallest wavelength would be the highest frequency, you see. So the largest would be the minimum frequency. Minimum frequency is threshold frequency. Yeah, we are correct. So now it says calculate the frequency of the monochromatic light that must be used to emit photoelectrons with a velocity of, now you see there's a specification of velocity, from the cathode. So that means we need to use our photoelectric effect equation. Ne. Sengiyayibona. Thengathi ufuna unipopanisa kodwa. So the photoelectric effect, it means the energy of a photon must be equal to the work function of the metal plus the EK max of the electrons. So this is the story. So now we know that, well, this is Planck's constant multiplied by the frequency that we want. Work function is usually the Planck's constant times the threshold frequency. Ne? So this is going to be Planck's constant with F sub 0 there, which is threshold frequency, plus this one is half mv squared. Of course, the velocity being the maximum velocity. Nice and easy. So obviously, guys, what are we looking for? We're looking for the frequency of this thing that will give us that thing. Ne? Yeah. So since we're not given the work function, so what we calculated here was the threshold frequency. This will help us get the work function of this thing. So we can easily say, okay, what is Planck's constant? 6,63 times 10 to the minus some change. 6,63 times 10 to the minus 34. Okay, so we've got 6,63 times 10 to the minus 24, no, 34, times the frequency, which is what we want. Now this would be the work function again. This is 6,63 times 10 to the minus 34 into, now we found this frequency to be 1,31 times 10 to the 15 hertz. Plus half. Now the mass is the mass of an electron, isn't it? This is the one. It's 9,11 times 10 to the minus 34. Itheni ngathi khona into ezafuna ukwenzeka nje. Kukhona into eyenzekayo. So this is 9,11 times 10 to the minus 34. No, 31. Himan 10 balinte ngekhoyo. Sendinwe lawe. Hayi man. Okay, ingathi kufuneka simove yonke into futhi kancinci. Ispace andisenaso, guys, so we need to squash things a bit now. Every potential space we can find, we must use. Okay, so now we want to accommodate the velocity here. What was the velocity? Is 1,57 times 10 to the 6. Now that is squared, okay? Very easy calculation. So therefore our frequency is going to be this side, which is 6,63 times 10 to the minus 34 into 1,31. 31 la, yeah, times 10 to the 15 plus, maybe we can just write it nicely and say this is 0,5 into 9,11 times 10 to the minus 31 into 1,57 times 10 to the 6. Is it 6 or 8? 6, all squared. This is all divided by the Planck's constant, which is 6,63 times 10 to the minus 34. Now we just want to end the pain, okay? And burn that shot in light. Let me put the left one. Now this one is 1 now, 6,63 times 10 to the exponent minus 34 into 1,31 times 10 to the 15. That one is positive, so be careful there. We're going to add 0,5 into 9,11 times 10 to the minus 31 into 1,57 times 10 to the exponent 6 all squared divided by 6,638 times 10 to the minus 34. Yeah, yo. Hayi ininzi la frequency yayibona. Ithi ngo-3,00 times 10 to the 15. This is as good as just 3 times 10 to the 15. So this is 3 times 10 to the 15 hertz. Can you see? It's higher than that threshold there. Of course, this was because we had a specific velocity that we wanted. So, to get that velocity, we needed a much higher than that threshold frequency, because this one only strips electrons, but they don't gain kinetic energy. So we need more for them to be stripped and to gain kinetic energy. So that makes sense. It doesn't look too different from that one. So of course the photoelectric effect equation, nice and easy. And then of course this is the calculation of the work function. This is the calculation of the what you call kinetic energy, and then of course the answer. The substitutions here do not really get the marks, unfortunately. Remember, substitutions may or may not give marks, but the advice is that please show them so that if ever they are recognized, especially if your answer becomes incorrect, then you can score marks for the substitution. If it's not there, then you lose marks. That's the story. Anyway, guys, let's go on to 11.5. Now 11.5 says, how will the answer in question 11.4 change if the largest wavelength of the monochromatic light needed to eject electrons is reduced to 1,89? How will the answer change in this one? If this one is less, remember this one is more, this one is less. Write down increase, decrease, or remain the same and give a reason for your answer. So this is one of those silly questions, you see. Of course, these ones are higher grade questions. You can't just run around and just, blurt things out that you don't understand. Okay, maske think. If the wavelength decreases, so that means the work function of the electron, what is this? The work function of the metal also will be less, right? Right. Now, it says now, how will the answer we got? Of course, that frequency would also be less, isn't it? Yeah, it would be less. So it will decrease. Hayi andazi maske siyibhale kanjalo, it will decrease. Masibhale la decrease. It will decrease. Now let's find some reasons why. Maske sibone this equation. Now think of this as some model of equations in maths that you know. What do you think this is? What does it look like? What does it look like? Because now, what are we trying to look at here? We're trying to compare the threshold frequency to the frequency of the light needed. Can you see? Given this specification here, and we saw that, well, if we keep the kinetic energy constant, we are saying this thing is a constant, essentially, because we have not changed the speed of the photoelectrons that we want. And yet we are changing the threshold frequency. If we're changing the threshold frequency, of course this is a smaller number, so this means this one will also become smaller, isn't it? The threshold frequency becomes smaller. So remember, wavelength is inversely proportional to the frequency, right? If the wavelength is more, then the frequency is less. If the wavelength is less, then the frequency is more. So the frequency is increasing. It will increase. So this one is increasing. If the frequency increases, now remember, Planck's constant is the same, right? Right, so this one is also a constant, so we can mark it this way. This one is constant, and that one is constant. So literally, this is more like an equation that says y equals mx plus c. Because this is constant, this is constant. Now we can explore the relationship between those two. Obviously, we could see that if we increase the threshold frequency, this means the work function is going to increase. Then we'll need more. We will need more. So this means this frequency must also increase for this to balance out. So our answer is wrong. Because we can see these two are literally directly proportional, or we can easily see that as this one increases, keeping this the same, that is the same, that is the same, then the frequency will also do the same. It must increase. So we need it to increase actually. The mathematical models, they help out, because we know that, well, yes. Remember here that this does not accommodate negatives and stuff and what. Everything is increasing here. So this is a graph that says if x increases, y will also increase. Okay, nice. You see what makes it a higher grade question? You need to think about that. Honestly. Sorry, so we will rewrite the answer now. This increases. So you see, sometimes guessing is not good. Is not good. Now the explanation is that well, the frequency of the light necessary will have to overcome a higher work function this time. I don't know, guys, to give a reason. So we will say the work function, with a lower wavelength, it means the frequency will be high, and that would mean the work function is going to be higher. So we'll need a light with higher energy to overcome that work function, so that we can achieve the same the same velocity of the electrons. So I can say to you and to them is that, well, with a lower wavelength, of threshold, with a lower wavelength required, they would, and then but I give a reason. Sometimes we need to be careful. Give a reason and explain is two different things. Sometimes you can look at it the same way, but what can you do when you don't know what to say? Just explain, okay? Now, with a lower wavelength of required light, or wavelength of light required of light required, the frequency will be higher, necessitating sibhala isingesi ngazosiqhela kabi, asange siyodlala esikolweni thina, sasiyofundela isingesi basikwazi usisebenzisa, hayi nje ukugwajisa abantu ngaso. Will be higher, necessitating bhalwa kanjani? Necessitating a higher frequency of imminent light, to overcome a higher work function to achieve the same velocity of photoelectrons. Ish. Specified. Yawena. Ibona yengo. Siyakulimaza specified. Hayi siyasithetha isingesi bafethu khane siyekeni. Ingazodlalela ukuthi yabona ngoku bendingazi ba ndizawubhuda ngithini bafethu. So at some point ezinye izinto ziyabheda. So what we are going to say, I mean, it says give a reason, but I'd rather it says explain your answer, because I don't think it's that easy to give a reason, because there's two terms on the right hand side. If there was no terms, we could talk about direct proportionality, but we still can if we keep this constant anyway. So because that would be direct proportionality, as you would evidence by a straight line passing through the origin and stuff. So but now we have a y-intercept. So if we've got a y-intercept, it means this doesn't pass through the origin. So of course direct proportionality will not always pass through the origin. Sometimes it can do this, but it's okay. It's alright. So I'm not too sure if it would be nice to say direct proportionality effectively so. But obviously this tells us this is the minimum we can get of what? Of the kinetic energy, because that would be the minimum kinetic energy we can get here. And then there can be more depending on the frequency if it's increasing. This is when we're plotting frequency against kinetic energy. Okay, stuff like that, because that would be the y-intercept in there. Now guys, I'm trying to think, ndivele ndachaza, but maske siyeke kanje sithi ya-increase sithi yonke le mbudane sibhale pha sizayinika 2 marks, because what do you do when you don't have a clear reason? Because I'm trying to run away from saying the frequency of the light needed will be directly proportional to the threshold frequency of the matter. Maybe, and since this will increase, this one will also increase, keeping the kinetic energy the same and the Planck's constant the same. You can use that route to explain this, but I think it would be slightly dangerous. I don't know, whatever. You say something that makes sense. And I think this argument is, did I say imminent? Actually, I wanted to say incident. See, refine. As long as better, as long as imnandi, what is better? Incident. Now that's physics. Imminent, it's impending doom. It's something that is soon to happen but has not yet happened. But this one is incident. It's actually happening. You understand? So be careful of the language. You know, it can do things. It can do things. Alright guys, so this is the end of our argument. Crazy as it may have sounded, but we could easily have taken these 13 marks nicely. As you can see, the last question is definitely higher grade, because you need to think of a mathematical model here where we've got y equals mx plus c, knowing that this is a constant, this is constant, and the variables that we want to assess is these two. What happens when the other one changes? How does it influence the other? You see? So these are some of the things you need to be smart about. And you will hardly be told these kind of things directly like this. So this is what makes these YouTube channels very unique, because you get explanations that are even based on experiences of people from different spheres of life, now realizing the utility of maths at metric level, that it's not a joke. So don't listen to fools fooling around and making you fooled as well to suggest, this education is weak, it's weak like 10. Can you see that even the things that you learn have a very wide variety of applications in real life? So don't allow people to nullify what is good. But yes, we agree there is a problem with the delivery of this very same good something. The delivery is wrong, okay? I will say that without even flinching. it's wrong. Because first of all, you are influenced to cram and reproduce and regurgitate. That means this already sets you up for no understanding whatsoever. So you will never have a deep understanding when you regurgitate stuff. Okay? It's like food. When somebody regurgitates food, that food is undigested. It hasn't been assimilated into the body. It's really coming out the same way it went out. You get me? And so that means you lose the nutritional value of food. But you see, when you when you that food, it has changed. It has been modified. There has been absorption. So you have gained from it. Do you get me, guys? So don't regurgitate. Please, 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 please. Make an attempt never to do that. But some situations when you see you are failing, especially at university, at matric level, I would discourage this heavily, because passing matric without understanding is already suicide, because wherever you will go, you will struggle straight up. Unless you will find some luck and get the same methods you found, maybe you'll make it, but again, it will become a disaster for the future. Because remember, everything you do now matters in the future. It doesn't matter in the near future. It matters in the long term. When you are a professional, you are working, you will get a job and get fired because you're failing to deliver. You know why? Because you don't have the knowledge you need to possess for a graduate. You get me? And again, as you work, you need to amass experience, flexibility, deep understanding, because the more you grow into the field, the better you should become. You should not stay the same. You can't be constant, because things are changing. Some of the older versions of what we used are no longer useful, because obviously these were nothing but approximations. Now we need exact fits, because there's no time for play and waiting for things to get better. We have to get them right now, or else everything gets spoiled. Ne. So bafowethu sibamba khona la. So I hope you guys enjoyed this review, and please guys, practice this paper. Try every question before you watch me work it out, so that you can understand the thinking behind the generation of these answers, and you can see the skills necessary to navigate different types of questions. For me, I feel like this is a paper that completes the very revision of physics, because it covered most of these topics properly, because it provided me even a way to educate you further. All right, so I do hope and believe that we are in the same spirit. Of course, guys, if you spot some issues here, please do let me know. And essentially, you can comment also on your approach, which one you chose. Maybe it might be concise and even better, maybe even more exact than mine, which is probably approximate rather than being exact. So especially a question of this nature, because remember, I chose to explain and yet I'm told to give a reason. So there's usually a slight difference between the two. It's like dark and gray, you know, it's a gray zone basically, because I'm looking at the marks and I know I have to make sense in what I'm saying. So if you capture the fact that a lower wavelength will result in a higher frequency, and that would also make the work function higher, then it means we need to have more energy to overcome that. So definitely that frequency will have to be higher. So that's making sense. Of course, I've made sense in many words, but you can make sense in a fewer words. Refine your language. Do summarize, but do not leave the science outside your summaries. It's very dangerous. Okay. All right, guys, I hope you guys enjoyed. And of course, I'll try to make you guys a video, maybe later tonight. It probably might premiere before even this video. You may have seen that video before this one or even after this one, but I'll make sure before the end of tomorrow. In fact, before the end of, let's say before evening tomorrow, I'll make sure you have this video. I'll make a video where I sort of try to dispel or demystify, you know, how to deal with MCQs. Because unfortunately, I cannot do many question papers at this point. It's too late, guys. I don't want you captivated on watching videos that may not be relevant. I want you to watch a video that is comprehensive, At least that is the better view, which is what I tried here. I didn't try to speed against time, but I tried to take it as slow as possible to actually give you a proper overview of what you need to have to go and pass in that exam, and also what skills must you possess within you. You could see that some questions like that thingy, what is that thing, talking about the internal resistance. You see, sometimes it's not something you're prepared to answer because you may have ignored or overlooked the definition because it's not commonly asked. But you need to show that you understand its significance. As you can see, you need to be a bit flexible. You can't just rely on cramming, because how many things can you cram, guys, and still have logic being applied at the same time? Those are two things that don't go together. Cramming and logic don't work together, believe me. It's a fight that will leave you blocked in the exam, and then you'll realize later and be like, so don't even attempt cramming. It's not necessary. It's not healthy. It's bad, actually. And as you have seen when I explained how bad it can be. Okay, so folks, I will see you again some other time. Give this video a thumbs up, share it with your friends. Please revise. There's plenty of videos in my channel. If you need more of what you have just seen, in case you feel like you are hearing me but you think you want to hear more, there's more videos where I have done this, and I've done it in a similar manner. And each time I'm trying my best to bring it alive rather than to just keep repeating myself like a broken record of some sort. So that's just the idea. We need to keep growing, we need to transform, and we need to get better. Otherwise, guys, good luck for your physics paper 1. And please, 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 guys, watch the MCQ section of this video. Watch the MCQ section of the video I've done for 2009 especially, because that can give you the feel of the skills you need. And then, of course, I'll try to highlight these in a separate video to show you that this is what happens in the MCQs, and you need to be at that level. Of course, I'm not going to have a proper plug and go type of a thing, but I will give you something that makes you sit very comfortably when it comes to MCQs, because it means even if you didn't get 20 marks, you will not get any less than 15 marks. You will get 15 and more. So you need to be within the last third of those marks. So yeah, that is the story. It's a pity, guys. I had a video with my students last night doing this paper. Of course, we didn't finish it. We stopped at the end of mechanics because it became too long. It already took 3 hours. But at that time, I was trying to engage my students to actually suggest ways in which we need to solve this, because I need them to be in a way of knowing how to plan on their own. I was just playing a role of a facilitator just to confirm or even suggest more. Okay, so that was a very nice video, and unfortunately, I don't know what happened to my screen recorder. It just kept my screen of Google Meet instead of recording, so you wouldn't see anything I'm doing. You can hear us talk, but you don't get to see what we are doing. So I actually deleted that video because I had uploaded it hoping to share it with you guys, but then it didn't work out. So it seems my technological skills need a bit of more work. I will find a way of doing it next time. Of course, that would be for the ones next year, because already this is the end of the road for those of you who will pass and move along. But those of you who will still want to do this again, this is going to be of benefit, I hope. Otherwise, I will say again and again, I will see you when I see you. As long as the Lord is willing, we will definitely meet. But do your best. Believe in yourselves. Please do the actual practicing. Don't just watch someone doing things. It looks easy, but when you get to do it yourself, you get stuck. Okay? So don't do the injustice to yourselves and just watch. Rather, actively watch, meaning pause, try, then watch. Pause, try, then watch. Then you'll start to see how many ideas will start to reveal themselves to you, even beyond just what you are seeing as an explanation. Because you have thought of something, you will even start to develop different techniques within the same setup. And that means that's a fruitful interaction. And that could even be enough to just go into the exam the next day. But make sure the definitions, at least revise as many as you can in the morning of the exam, so that at least they are fresh. So yeah, just do that to yourself, for yourself, and you'll be fine. Otherwise, guys, yo, andizeni papayise ne papayini ndiyanithanda nonke bantram nabo tatso nabo buto, because abanye benu, they are my age, they are upgrading, and others are even older than me. They're my Grotmans and Sesterikis, and others are Uoms and Tanis, and others are even my grannies and grandfathers. But remember, education, you never get old for it, guys. You can educate yourself even at 60 and still achieve something. Trust me, your heart never dies. Your desire for growth never dies. So keep it up, keep going, and keep going. Just keep on going. Even when the going gets harder, keep on going. But also strategize, plan. Sometimes do a hard question, alternate with an easy question, so that you keep the pace while you move along nicely. Because the easy question motivates you again, it gives you the oomph, it also makes you, salvage time for yet another tough question, or even that one later on if you didn't finish it. And then you keep doing that until you can't do it. Then you do the best that is left of you. Good luck, guys, and goodbye. We'll see each other probably tomorrow on that video when we try to look at the MCQs. I won't make it long. I'll try to be as practical as possible. So probably it's going to be less than 20 minutes. We'll see. Until then, goodbye.